Well, I want to thank everybody. These are, look around and look at the people who are around you. They're the hardcore cases that didn't stay up all night long drinking. Welcome to the final day of the ATC. Wanted just a couple of things to remind you if for any reason we get a fire alarm or anything, the assembly is out in the parking lot in front of the Hilton. The second part is the scoring sheets. If you don't have a scoring sheet for today, they are back there on that back table. Please, please, please score, because that's how we are going to be able to get the first, second, and third place for the papers. And that's important to the people who presented. When they win first place, they look at all the other peers and say, yeah, 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 yeah. So, okay, get this thing started. Mr. Paul Bernard is going to be the session moderator. And thank you again for your attendance.
Good morning. All right, our first paper this morning is authored and presented by Lucas Bimmerly of Siemens. The title of his paper is Data-Driven Optimization of Overall Analyzer Effectiveness. He claims that the hotel printer wouldn't print out his bio, so I can't read it, so he's going to have to tell you himself what he's done in his, 20 years, 21 years? A bit older, okay. Anyway, here you go. Let me get this thing lined up. Testing.
1, 2, 3. Oh, it's working. Okay. That works as well, right? Okay.
Good to go?
Yeah, I'm good to go. Yeah.
Okay, you put it in presentation mode.
So good morning, everyone. So I think the situation and the printer didn't work is, I think, a really good starting point to talking about digitalization, right? Talking about reducing paper, but that will be not the focus for today. So I want to talk with you about how we can use data. So data are the most important information we generate with process analyzers for the process. How we can use different data to optimize the value we're generating with process analyzer, to optimize the performance and optimizing the maintenance. So my name is Lucas Bimmerle. Lucas is fine, I know it's a hard name in English. I'm from Siemens and I'm started as product manager for service for continuous gas analyzer, laser and gas chromatography. And it was 8 years back, and one of the first things we done was to talk about remote connectivity. And remote connectivity was this time something which everyone said, that's a very crazy idea, right? Or we will never access remotely to any plant. And I'm still thinking it's sometimes a bit crazy in many locations, not possible. Over time after COVID, it's more and more acceptance. And the same applies then, and I took then over additionally the role to drive our digitalization portfolio there, with focusing on connectivity, on software, and on data science for every kind of process analyzer in the field. And that's basically what we are doing. So I'm consulting customers worldwide how to implement digitalization solutions in their plant, how to design them, how to drive them, how to make them successful. If you're looking into the typical pain points, you will all know from your daily life is we have three main issues there. The first one is always how we keep the equipment in operation, because we are faced with unexpected device downtime. We are faced with problems every day the technicians has to solve. And of course, on top of that, from a process perspective, there are more and more requirements coming. So you have to get higher availability every year, and in best case, what they expect with less costs, which is really critical to achieve. The second topic is, of course, how can you maintain your analyzer? You have various technologies installed there. You have to train your people to know about what is the typical issues of each analyzer, how you can do higher efficiency in maintenance. These are topics, of course, you are facing. And the last topic is, what is the transparency? Yeah? Where's the transparency? You have, of course, to prove which analyzer is performing good or bad, because at some point you have to decide which analyzer you want to substitute, because it's maybe running for 20 years, but maybe some of them are running good, some of them not. Sometimes you pick the right vendor, sometimes not. Sometimes the application had some issues. So you have to try out and to define, okay, where to start. And often we are doing it right from a daily feeling and from, okay, this analyzer is going weaker and weaker every year. So we have now to initiate that. And that is, of course, a challenge. And additionally, you are all faced with the situation that if you want to purchase new analyzer, you have to talk to your purchasing department, right? And then the situation comes up. They maybe not pick the one you want to have it in the plant, which is the best one. They want to just look into the price and get the cheapest one. And after that, you have the biggest issues on your side. So of course, you have also to find a way how to convince them, to prove to them, okay, maybe I purchase the other analyzer, but it will work over the next 15 years far better than the others. It has more value. So the question is, how can we address these pain points? And of course, we are doing already, or you are doing already many topics daily: preventive maintenance, investing in new modernized equipment, training your people, qualification metrics, getting the people to experts, analyzing more information, and so on. So what is my thesis or my approach? I see that we have to use the data we have in the field more than today. And we look later on which data you are normally using there and which data we are not using there. If we are using data and collecting them over a long time, we create the transparency, how good the analyzer are performing in the field. And this is the starting point where you, from the perspective of reliability, can really systematically improve process analyzers in the field. If you don't have the data, you decide that based on individual perspectives of analyzer. Maybe there's one expert saying, this analyzer we have to substitute, but if you're looking on the worldwide perspective, maybe not the knowledge is there everywhere, so you have to compare different type of analyzer. We see that still, and that's a clear message for today, digitalization, and that's really a buzzword, yeah? It's not about just to make digitalization, right? It's just to make tools for technicians and engineers in the field to deliver better performance for the analyzer, to make their life easier, to give them additional possibilities how to do their job. So preventive maintenance routines and analytics experts are, of course, the foundation of all of that. But if we're looking into lack of resources there in the field, we need to get our experts in such a shape that they can do their stuff easier than today and they can really focus on the right task. And the last topic, and that's my thesis, we see that data analysis tools will be getting more important every year in the future. We want to use the data to optimize our analyzer, and it will be a state-of-the-art tool for every technician and engineer in the field. So we have to try it out. And if you maybe start to looking into your individual perspective, I think every one of you uses an application in their daily life, right? You have it all, a smartphone, you're looking into applications, You're maybe tracking how much you spent yesterday evening in the bar. You maybe check how fast you or how far you walked this day because you have already, due to the high amount of eating in the last couple of days, have to walk a bit more, so you're also tracking your performance here, right? But of course, if you now look into your individual perspective in the plant, you can maybe ask for yourself which tools you're really using there, yeah? Do you have a transparency of the performance of the analyzer or not? So let's start with the topic, and for me, the driver for digitalization, the driver for everything we are doing is reliability. We want to achieve a higher degree of reliability in the field. And I took the one definition from the American Society of Quality. There are really more definitions in the field. And it's saying that that reliability is the probability that a product, system, or service will perform in its intended function adequately for a specified period of time, or will operate in the defined environment without failure. So actually, that's what we are trying to achieve, right? We want to ensure that our analyzers are exactly fulfilling their purpose to deliver trustworthy measurement results to a process in a consistent way. So all the time, in best case 24/7, without interruption. So we are doing preventive maintenance, we are keeping spare parts in the stock, we are doing modernization to optimize the reliability of process analyzers. And we see that process analyzer, it's not that easy, right? It's not a device, it's a system consisting of many various elements, many various factors. So it's not only about time of the process analyzer. It could be that the accuracy is too low. It could be that you have issues with sample preparation. Your shelter conditions are not stable, so the ambient pressure is changing. So it's all influencing the reliability of analytical measurements. So what we define, or I defining reliability, it's a combination of the availability of the device, so which we can track with alarm and warnings, with the internal device health parameter, with the measurement quality, which we prove with frequent validation and, if necessary, calibration, and with measurement stability, that's what I call it, about the sample preparation status and the shelter status. And all of that influence the reliability of analytical measurement, and this is in the end the measurement performance, and we providing based on that value to process control. So the question, of course, which picks up is how do we track reliability? And I mentioned it's not only about availability, it's more than that. And I find it quite hard to find really a KPI which is proving that. So most of the KPIs in the field, they are only talking about mean time to repair, maybe availability, but I don't think that's a really good fitting KPI because it's only talking about a specific aspect. So what I'm proposing is one KPI, which I think is a good one to look into that. It's the overall equipment effectiveness, which is well established in the field of machines and assets in the field, which is describing the degree of productivity of any kind of equipment. So now using this KPI, which is more used on the machine to transferring to analytics, of course it meant that we have to consider some of the elements, and it's availability, quality, and stability there. And with this information, we calculate the overall analyzer effectiveness, and later in the presentation you see a calculation for that. And in the end, based on that, we can track, if we compare it with the cost, how much value add we generate with each invested dollar into our process analytics. And we need that to prove the investment to the management of the plant to argue why we should invest in process analyzer. So if we are looking into data today, we're mainly using only limited information. Your process control system is using the measurement values and sometimes alarms and warnings, even if the process people cannot really deal with alarms and warnings from analyzer. That's weird stuff for them, right? But if you're looking into other information, there are a lot of possibilities there. Of course, the validation and calibration results there. You can get the information from the shelter environment, yeah? For example, the temperature there, the pressure there. You can get information out of sample preparation systems, so if they are smart, providing pressure, temperature, flow. You can even get information about the pressure in the reference gas bottle if you have a sensor there. And you can get out from every device some diagnostic information, which we will see in the next pages, which you are normally using if you're doing troubleshooting. So imagine a gas chromatograph, you do a troubleshooting, you go there to the gas chromatograph, you may be looking onto the response factor, retention time, on the chromatogram and so on, but you're not using it in a continuous way, right? You're using it if you have a troubleshooting. So we see that we should do, or we should use all this data to optimize the performance of the analyzer in the field. So let's talk about some examples to make it very concrete. If you're talking about measurement availability, it's about the device, right? So if the device fails or not. So of course, we are collecting the current status of the device, the alarms and warnings, and different diagnostic parameters, which are getting more and more enhanced into the newer devices there. So there are a lot of data which are provided. So the availability of this data depends really on each analyzer in the field. What we are doing as an approach, and I experienced with my team in the last couple of years, that there's a specific way how to use this data and how to analyze this data, because it's not about monitoring. If you start to monitor every diagnostic parameters you have in your analyzer, you have suddenly 3,000 parameters somewhere in the software. No technician at all will ever read them out. It's far too much. So it's about how to use this data intelligent, yeah? That's the way to do it, because you don't have the time to look every day on the software, every minute. That doesn't bring you value, that's causing only time for you. So what we did is to identify ways how we can analyze this data automatically. And the typical things we are seeing there is that the user defines a limit. If the temperature is too high, creates some alarm. But we're also seeing more a statistics-based approach. For example, to use the statistical distribution of data to say, okay, where's the outlier of this information? To identify drift of this data. So if there's any kind of increasing, decreasing curve, specific pattern, if the points are fluctuating heavily, it's also an indication that maybe something is changing there. And also, what we see as very important, that you put these parameters in correlation. Just looking into one value will only in some cases bring you value. So we're seeing always 3 different ways to go. You have an expert defining a specific rule for a specific parameter. You're using basic statistics there, or you're using the field of artificial intelligence to use it. And in the end, you calculate with that information the availability of your device, which you can then track as KPI. Now let's talking about concrete examples there. And I brought 4 of them for 4 different technologies with me. But of course, the same approach you can apply for every analyzer. If it's a TOC analyzer, pH sensor, conductivity, it's possible for every device. You have to look into the individual device from each vendor, what is possible. But now let's talking about an oxygen measurement we have. So paramagnetic alternating pressure technology here. We see that there are many topics which you can really address already with pulling out this data there and evaluating them. So typical issues we see, we have pollution there in the oxygen measurement there, in the measurement chamber. We see sensitivity loss of various sensors, but in this case a microflow sensor, defect of pressure switch, defect of electronics, problem with the housing temperature, and so on. And one of the examples we had is the sensitivity loss of the microflow sensor. So the microflow sensor is actually transferring the cross flow which exists when the sample gas and the reference gas are meeting each other, and is converting this cross flow to the electrical signal in the end. And of course, if the sensitivity is going down, that means that you have a weaker measurement result. So what we have done here is actually to just put in a specific limit there. So a very basic approach. You have to know where to place the limit there. So you have to put the work with statistics, but if you have done it, it's a pretty easy to use functionality. But the challenge was that we have to use also validation or calibration as a reference for this logic there. So our system or this software has to collect during the validation every second data and make a mean out of it. So that was a bit of a challenge here, and we needed experts to build this functionality. But all these use cases just mentioned, which is mainly covering all the physical components of an oxygen measurement, or in this case, this technology, you can really reduce the downtime. Same applies for NDR technology. Typical issues, sensitivity loss of the infrared light source, any kind of issue with the sample chamber, chopper frequency issues, electronics problem, and so on. And in this case, we have a sensitivity loss of an infrared light source, which will always happen if you're running an analyzer for 20 years in this technology. And what in this case we have done is an analysis of the degree of the drift. So if the drift, there is always kind of a drift over time. But if the drift was increasing, that was a sign for us in a specific, speed that we have now to react, and a user has to get the information that he needs quite soon to replace the infrared sensor, infrared light source. So that was a really good approach there, and this this statistical rule is transferable to any kind of other device as well. Same applies also for TDL in the end. So you have also some problems there. Your window is polluted, the intensivity is going down, you have detector topics, the impact of the temperature. As well, we are now doing just a limit evaluation of a transmission parameter we collected from the device. So the main challenge was that this device has to provide this information to us, and then it was possible. Gas chromatography. Especially gas chromatographs are providing already today far more data that you can actually process. So some of the devices are capable to provide 20, 30, 40 diagnostic parameters to a software to analyze them. And in the field of gas chromatographs, you can actually also cover all the physical components there. So of course, all the peak characteristics we have, retention time, response factor, but also how good the separation column is performing, the detector sensitivity, the valves, the electronics, and so on. So what we have done here is to measure the peak resolution there, which is the relationship, actually from the peaks, how far they are from each other, and if they are starting to come closer to each other and starting to overlap in a specific degree of overlapping, then it's getting critical for your gas chromatograph in the end. So what we have done here is to measure this peak resolution there, and then if it's violating it or it's going down a bit, to inform the user that he has either a contamination of the separation columns or the separation columns has a wear process there. So it's also easy transferable. It's just a poor understanding of gas chromatography you need for that. Now let's talk about benefits, what we see, and we have done we saw an example with one of our customers in the field there, and normally we had the issue that he has a problem and that all the service issue starts because first he didn't know really much the device, so he has to find out what is really the problem. So he has to react, he has to extract the information of the analyzer, he has to contact the technical support and so on. So it took already a day until something could be initiated. Then it was needed that a spare parts is sent out and a technician or repair in the field. And of course, in some countries, it's possible to get maybe it overnight or in 2 days. But in some countries, you need to wait 1 week or 2 weeks for a technician. So it has caused a lot of downtime. So the analyzer was all the time not available for the process, which of course was a problem. If we are doing in a predictive maintenance approach, we get the information 2 weeks earlier, knowing that there will be a problem upcoming, The service technician can order the spare parts in time. The analyzer is still running perfectly, no problem at all. Then the spare parts arrive at site. There's the technician, can replace this part. You have maybe 2 hours downtime, and that's a big difference for you. So the analyzer's availability is highly increased instead of maybe 1 week to only 2 hours device downtime. Second topic, measurement quality, often underestimated topic. What we see is how to use validation results there. So what we normally see in the field is maybe you do a validation, sometimes manually, sometimes automated. You are checking for deviation of with a reference gas, for example. But in some cases, we also see more enhanced approach in the field. So one of the topics is a classical deviation pattern there. So if you have some consecutive increasing points, some decreasing points over time, some fluctuation, that already shows that there's an issue. Using a standard, the ASTM D699 and 3764 are the standards to go. So we're using here purely statistical approach there to analyze this information. There were a lot of papers in the past about the importance of validation, how to evaluate them in the last ATCs. So I didn't focus on that topic this way, but really a short explanation what we see. In this case, we've done a validation every day, which depends, of course, of the technology. So in some cases, you do maybe validation every week, every day, sometimes even less. From a statistical point of view, it would be good to have a frequent validation to really make sure that between 2 validations, the analyzer is still performing good. So what we have seen here is that the deviation of the green points you see here were still good, right? So no limit was violated, but we see a couple of consecutive points already which are above the center line, which is already an indication to look into that, because normally they should fluctuating around the center line in quite of a systematic way. Then after 7-8 validation, you see that now the values have changing a lot, right? So there was a high spread of the data there. So the repeatability was going weaker and weaker. And then already you see then you have suddenly out points which are violating limits there. And normally a technician would only see if a limit was violated. What a software can do is analyzing this complete pattern before already and inform a user that there might be a problem, so you can start earlier to investigate where the issue comes from. So this is the way really to look onto the quality, or often called accuracy of a measurement, but also to better plan your preventive maintenance schedule there. Last of the 3 topic, which I call measurement stability. You can call it whatever you want. It's about sample preparation, shelter information, and so on. So often not available, sometimes available as a sensor information. If it's available, you can use the complete approach for here. What we have done is here is to using artificial intelligence on it. So not using only statistics or only limit. So really did artificial intelligence on it. And we are tracking this information also within CPK, which is actually do a correlation between the specification limit and the mean of the value and the standard distribution. So if we look into the data analysis approach, what we have done here is we have done here a linear regression. So what is a regression in the end? So we are collecting all the data, historical data, and then this IA function tries to define a linear curve between these data points to be as close as possible to all these data points there. So it always adapts every second when a new data point comes into there, the linear curve, and based on that, it can predict where the next data point should happen. So it's a prediction possibility here. And we have used that to solve an issue for a continuous small drift within the sample preparation. So we have a loss of pressure here. The pressure was always between the limits there, but it was decreasing over time. And this was, the issue was in the past that you have to wait until the limit was violated there. But that was a problem because you have already maybe a problem there. So in this case, the software can tell you, oh, I see a drift here. You should look into the sample preparation, and you can act far earlier and solve that issue. Of course, there are other possibilities there to identify any kind of outliers there for various artificial intelligence functions there. So I didn't go in detail on this presentation there, but surely we can catch it up later what are possibilities here. All this information are influencing the overall analyzer effectiveness, which describes the performance of the analyzer. So in the end, if you have a 90% availability of your analyzer and you're tracking the KPIs for the validation and the stability of the measurement, and you might have a validation and a process APK from maybe 1, which is actually not so good, to be honest. Yeah, maybe 1.3 would be the way to go. So you have here 90% availability. You transfer the CPK to 95.3% and also the process CPK. And then the overall analyzer effectiveness is only around 77%. So only 77% of your time of the analyzer was really providing helpful information to the process. So I will sum it up because I'm running out of time. So we see that the overall analyzer effectiveness as one KPI to track the performance of process analyzer. It could be many other ways to go. But what we see is if you install a software, there's a discussion about the return of invest. You have to prove that. And only to do one remark there, many vendors are claiming you can save costs, maintenance costs. I would reject that if I would be an end user. It's not about cost saving, and you would reject that management bullshit discussion. Yeah? You should talk about how you can save efforts for your technician to focus on the right analyzer to optimize the performance there. Because the main benefit of digitalization here is to optimize the overall process. Because if you're having a higher availability and a higher accuracy, if you only optimize the process by a small percentage, you have the return of invest within 2 years or maybe less farther. So actually, I would come to the end. So we have identified in this paper a KPI to track the performance and the reliability of an analytical measurement. Data analyzers can help you to better operate and maintain analyzers in the field. And this kind of more predictive approach will save you a lot of efforts in the field and do it more predictive. The last sentence there, if you want to start, be aware that this topic is new for everyone here, right? You can ask yourself how good you are in statistics and data analysis. Also for us, it was a beginning phase. So the implementation of such a solution needs to be done right, because otherwise you have a software you will not use, and then you have only invested in a non-usable software. But I think in the next year, this topic will increase step by step, and we will learn a lot. And maybe next year, we will already see what is possible with data science in the field of process analyzer. Thank you very much.
Any questions for Lucas? No? All right, thank you very much.
Oh,
We do have one? Oh, yes.
Hi, thank you. If you start doing the predictions with the linear regression, how much data points would you typically need to start doing that?
It depends really on the diagnostic value, but at least I would say you should collect around 1 day data points at least. And if you want to really rely on that, you should at least collect about 4 weeks, because then you have quite of a good data set point, because sometimes, of course, the linear regression is not the answer to that, right? If it's not a linear curve. So you have to really look into the process and the values you are looking into that to optimize that, yeah. So I would always recommend, if you implement a digitalization solution, start with collecting information over a month to cover different process stages in your process, and then start with this artificial intelligence approach.
Okay, thank you.
You're welcome. Other questions? If not, thank you very much.
All right. All right, the second paper this morning is entitled Streamlining the Use of AI Machine Learning in the Chemical Industry Using Chemometrics. I know that Brian had a co-author.
No.
You didn't?
No.
Wow.
No one wants to co-author with me.
I knew I'd get a reaction out of him. So Brian is the author and presenter. He is the president of Infometrics, the first company in the field of chemometrics, and has managed the company for several decades. He tells me this is his 9th paper.
It is.
9 papers at this event. So he's been doing this a long time. He has a PhD in geochemistry and has published in many different magazines and various industry repositories of information all over the world. In 2016, he was presented with the ISA Excellence in Analytical Technical Innovation Award for his work in the field of chromatography. Ask him about his cars. He has a nice car, at least one. He'll talk to you about it for hours. Anyway, thank you, Brian. Go ahead.
Okay, thank you. All right, well, I'm going to continue what Lucas just started off. So he was giving you, we're still in the data mode, right? But we'll get out of it eventually. So I'm going to expand on the topic of data analysis. And where Lucas was talking more about what's happening with the analytical instrument systems that are out there, I'm going to take the next step. So what do you do with the data that's coming out of those instrument systems and how that all gets impacted? And what I'll have to do is I'll have to admit that when you talk about something like AI, no one knows what that means really, frankly. So everyone uses it, including me. But essentially what we have with things like AI or machine learning, these are inevitable results of what's happening in the consumer products arena. So we're seeing things that are occurring now that will migrate into the process environment. So we'll start using them in refineries and chemical plants. And so the question really is, how soon is that going to happen? And really, how long is it going to be before the benefits outstrip the costs? So what I'd like to do here is kind of differentiate between, let's say, vision and hallucination, because there's a lot of both that's going on, and to provide a little bit of practical guidance on how you might be able to take some of this technology and utilize it right away. Frankly, you're already doing it. So if we're getting into the machine learning world, here's a question. So if all your friends were to jump off a bridge, would you follow them? Machine learning will tell you, yes, you should. Christoph, that's for you to do next. Okay, so there is information that is out there. The information isn't necessarily vetted for a particular application. So what you have to do is narrow things down. And I'm going to differentiate between broad AI and narrow AI. And I'll give you a little bit of a background for that. So the question is, where can we use this technology? And in the hydrocarbon processing industry, there are a lot of different places where it can be used and is being used. It ranges all the way from upstream for oil exploration, for exploitation issues, and as we get into the downstream, the processing of the hydrocarbon fuels that we use, the chemical feedstocks that we deal with. The technology is also used in retail, in transportation, in virtually every aspect of what we're trying to do. Because I'm only given a half hour and there's a hook out here somewhere that has my name on it, I'm going to focus just on the downstream side. So this is where really a lot of the money can be made in utilizing AI technology effectively. So I'd like to introduce you to someone that you don't know. There was a woman who was put in charge of all of IBM. She was the CEO and now is the executive chairman. She differentiated between the narrow AI concepts and the broad AI concepts. And if you get a chance, go do a TED Talk with Ginny Rometty. It's worthwhile. 20 minutes of your life, it'll be worthwhile. But so something like narrow AI, this is what we've got to talk about. This is what we're going to be using in the systems that we're dealing with. We need to be able to look at a particular application and pick the technology that's appropriate for doing the task that's at hand. If we deal with broad AI, well, it gets a little bit more complicated. So an example of broad AI is self-driving cars. And so there are a lot of little challenges that happen with that, and you have to kind of experience those. These are things that are tough to do in a refinery, for one example. So we're going to focus on that narrow AI. But the points that she made in the lecture that I listened to was this whole issue of assembling data. So we've got things that are coming through with the Siemens Amadeus. I want to make it Amadeus. That has more of a musical tone to it, but they don't listen to me. But we have, people spend most of their time just simply assembling the data that is necessary to do a particular project, and only about 15% of the time doing the project. So thinking about using AI technology, using chemometrics technology, if we can use that to avoid that period of time, we've just made ourselves significantly more efficient. So with that, we're going to rethink how we're doing our work, but also the technology that is being presented has to be transparent. We have to be able to describe it. It has to be understandable. It can't be magic. So when someone tells you, oh, well, we have the secret sauce, I'd run, frankly. We have a lot of different terminology that seems to get invented, and I think people don't get, I don't know, bonuses or publications unless they come up with a new term. Some of these terms are older. Everything has overlap. And the key thing is we need to be able to take pieces of technology that are going to exist in different worlds, focus them in on a specific application in order for this to be useful. And when we deal with the forms of machine learning or AI, they fall into three categories. One of these categories we aren't going to use, the reinforced learning. That is the self-driving car analogy. Where our technology is important is going to be in those next two, the unsupervised learning and the supervised learning. And unsupervised learning is just simply, we've got a whole bunch of data, we need to figure out what the heck is going on. It's a discovery process. We will find information that comes out of that that we have to diagnose ourselves to see, is this causing a fault in a unit operation or in a product? But we're just taking the original data and taking a look at that. But ultimately, what has to happen is that'll go into a supervised learning approach. And these are the terms that are used in chemometrics, in AI, and in machine learning. The supervised learning is where we're going to take that information that we collected originally, and we're going to make models out of it and use it to predict performance. Now, we do this using multivariate data, and we do that simply because we've got tons of data that are coming through. If you go and you put an optical spectrometer in place in a process environment and it starts punching out data, there's a tremendous amount of data that comes through there. You have to be able to process that. We have thousands of process sensors and probably hundreds of chromatographs and spectrometers that are in use in a typical large plant. And we have cheap processing power. So what we have learned is we've got technology like our phones that have more compute power than the first computer I ever used. And we have to recognize that we have human limitations. You are really, really good at recognizing small differences between two pieces of information. You are really, really bad at quantifying that. And you can't get information out of an Excel spreadsheet. It's just not possible. You don't see those patterns effectively. But computers can do that. And it actually leads to a shift in the goal of analysis. So now what we're going to do is say, what can we do maybe in a chromatography situation? It isn't so important to give the concentrations of the individual analytes that are in that stream. It's to understand whether that stream is acceptable to the customer that you're going to sell it to. And that's a little bit different. So what we're going to do is balance out how this technology can be used for sensors and for analyzers. And we're going to look at the process sensors, spectrometers, and chromatographs. So I'm going to go through all of it. With the process sensors, hey, these things are cheap, they're easy to install, they're quick to replace, the replacement gives you the same information. That's pretty cool. You've got a temperature sensor, I can put it in place, I can rely on it. One thing that happens with a temperature sensor, you get an answer. You don't get a quality of that answer. You don't understand whether that answer is actually accurate or not. It might be stuck. Well, let's think about an analogy. So let's look at a weather map. This actually is a weather map that came up in my region. This is Seattle. We're focused in on the Seattle, Washington area. And this tells you why you take a multivariate approach, why you take an AI approach, why you take a chemometric approach. We have a temperature reading right in the center there, so it's just on the Kitsap Peninsula of 74 degrees. The weatherman, Rich Marriott, looked at that and said, something's wrong with that temperature sensor. Well, how do you know? The way he knew is he looked at all the other temperatures that were in the region and he saw that was out of the norm for what he expected to see in the pattern of temperatures that were there. So you can flag anomalies on individual univariate sensors by taking a multivariate approach. And guess what? The information's already there and it's free. So let's look at it. How many people here are actually familiar with the field of chemometrics? I'll call it chemometrics, I like that. So we have we have a few, that's good, okay. For the rest of you, I'm going to teach you everything you need to know about chemometrics in the next minute and 45 seconds, okay? So all these people that say they know chemometrics, they're not, don't be impressed anymore. Okay, so what are we going to do? Let's just take two sensors. So I'm going to take two sensors, that gives us a two-dimensional work, just X and Y. What's the first thing that you do with this? I mean, you've done this your whole life. What do you do with this data? You plot it, right? So if we're going to plot it, the data shows up. As soon as that showed up on the screen, what did your eye do? You drew a line, yeah, exactly. You drew that line. That's the first principal component. It describes the maximum amount of variability that exists in that data. Now, this really doesn't matter if it's two-dimensional or three-dimensional. If this cloud of points were bees and they were coming out into the room, you could still find that first principal component. Now, here's where the magic comes in chemometrics. We can draw a line that is perpendicular to the first. In mathematical terms, that's called orthogonality. It's orthogonal to the first. So what that means is that the information contained on that second line is completely independent of the first. So now what we have is we have a new axis to look at data where the information content, the results that show up on each of those axes, is independent of one another. Now, for convenience, what we'll do is we'll just take that and we'll rotate it so that now what we have is the principal component diagram. So first principal component axis by tradition is on the x-axis, second is on the y. So with that look, remember each of these axes are linear combinations of every variable that you've put into it. So if we then look at that all by itself, the thing to know, and here's the importance of chemometrics, well, sure we have a trend, but if there are 2 points that are close to one another, that means that their measurements were similar to one another. And that's the basis for the whole field. So let's take a plant that's about 50 miles away from here, and we're going to just dump all the pressure, temperature, flow, and level information out of that plant. So we have 36 variables that were done 62,000 time points. If you wanted to do that XY plotting activity, you have 12,000 or 1,200, 1,260 XY plots that you would have to plot. So that would be tedious. But if you just look at this, we know that this plant is operating properly. We know that we had some shutdowns and startups, and we can see that in the data. We can also see where process stability is. We did this in minutes. So now the thing is, if you look at the lumps that are off, let's see, to you, it's on the right-hand side. It's not a uniform distribution. We seem to have different areas where process stability was there, where good products were being generated. This gives you a way of going in and looking at it and say, what were the conditions under which those things succeeded? Did they have different cost issues? Can we improve the process? This is something that you can do literally in minutes with about, I think, 75 different software packages. So you've already got it. So consider that you never just have one sensor. What you've got is you've got a bunch of sensors, and if you use those sensors, know the correlation, take the correlation out using principal component analysis so that you can identify the trends and the patterns that exist. That can give you an improvement to, say, a closed loop design. So now I'm going to move into actually the areas that are my favorite, are chromatographs and spectrometers, because those are the only ways that you can measure chemistry. You are selling chemical composition. You have to measure chemical composition. Chromatography measures molecules. Spectroscopy measures functional groups. It's fundamentally different. You think about that when you look at what instrument am I going to buy. But chromatography is just, it's an absolute workhorse. So it is probably the best way of looking at components that are in a mixture. So let's take this out and let's look at Google. So Google technology. So if you stare hard at this picture, that's a little fuzzy, right? That's the way it was taken. But it sharpens up. They can do that completely automatically on your phone. So and it hasn't hit on my iPhone yet, but so you have a way of taking and processing data automatically. It can think for itself as to how it needs to do that. Well, we don't take that many pictures in, say, a refinery. We do use chromatography. One of the things that happens with chromatography is you've got retention time variability. So can we apply the same type of this artificial intelligence to eliminate retention time variability? And in fact, you can. So there is a modification of voice recognition technology that has been applied in chromatography, and you can completely eliminate retention time variability after the fact. You can take old data and fix it. And if we look in detail at that, you can see that the alignment is good. Okay, so we can correct data. Now, how do we use that? The primary places, at least in a refinery operation, will be on detailed hydrocarbon analysis and simulated distillation. So let's look at an example with simulated distillation. So if we're in the laboratory, what's the first thing you do with a chromatograph? You run a blank. Why do you run the blank? You want to make sure you got a clean system. The next thing you do is you run a retention time standard. So it's a series of N paraffins. We happen to know what their temperature of boiling point is, so we're going to use that information to convert the x-axis from retention time to temperature. Then we're going to take, if that works, we're going to take a reference gas oil and we're going to run that through the system. And the reason we do that is we want to be able to check with a known quantity to make sure that the boiling point distribution is within the range that we accept. This is the ASTM procedure. This is fine. And then we can run samples. Let's go online. What can we do online knowing that we have retention time correction capability? Here what we can do is we can take we still need to run that blank. We need to make sure we have a clean system. The very next thing we do, we run samples. Now, why can we do that? Well, in the laboratory, we already had a retention time standard. We already had a reference gas oil. We can use those as targets to match the new data into the system, and you can get an accurate assessment of the simulated distillation points. So the boiling points are as good as you can get if you did the calibration directly. This was done with an ASTM study, so we did the round robin. We could take anybody's work and use it to correct anybody else's work. So with chromatography, we note that we don't have enough skilled technicians to handle all this stuff, so we have to be able to make them work more efficiently, and that the chemometrics technology is valuable for doing the signal processing, correcting the retention times, but then also you can use that to identify whether samples are out of bounds. And by doing this, you have, basically you can compare chromatograms from location to location and have a common interpretive base. So in the last bit, I'm going to go into spectrometers. We got a bunch of spectrometers that are here. And I'm going to go online in a different industry. I do like cars, so you know that the units that are used now to produce the cars start doing their own fault detection. So it's a little more like what Lucas was referring to. So they can determine whether they've got a part that's starting to fail. They can place the order and put it into the system in a fully automated way. Now, you should be able to do this at Marathon. I'm looking at your tag right there. Okay. So if we look at cars, we can take this and bring it down to the unit operation. This is a message that comes up on a Tesla's screen, and it says, an unexpected condition has happened. We've ordered a part and sent it to your preferred place for doing installation. Please call and make a reservation. This is in the car right now. Okay. We can get this information. The information is there for the picking. It can come through. And the last time one of the talks that was given, this was given by Chevron, so Will Warkington gave a talk at ISA-AD, so the predecessor that is now much improved and called ATC in 2019. He was talking about using spectroscopy in the refinery and said, well, okay, we like spectrometers, so they're relatively inexpensive. And you start saying, well, yeah, relatively inexpensive. I saw the price tag. Yeah, but look at the price of the giveaway that you just recovered, and it's a couple of months. So, but you can put the spectrometers pretty much anywhere, and they can measure just about anything. Ask any of the vendors. But you have to consider they aren't completely plug and play. So the long-term sustainability makes us say we've got to think about this a little bit differently. So we can do that principal component analysis, and we can look at gasoline samples, for example. So here's 6,000 spectra in a 3PC view. So this is a rotatable view, which I'm not rotating. But so you can see the bulk of the properties. You can see some special blends that were being done in this particular refinery. You've got a quick way of looking at data just by using principal component analysis. And you can take that into some of the feed functions too. Here, things that are coming out of reformers and that are feeding into a reformate splitter. So looking at different production pieces based on changes in things like temperature or even just the units that are being used. You can see deviations, you can see all the things that are going on. But ultimately with spectroscopy, what you have to do is you have to do a calibration. So you have to calibrate it for a particular application. Now that takes some time. For the people here who've been doing chemometrics, if you've done PLS regression to do that, you understand it takes a little bit of time. It actually, if you have an AI kind of system, we're going to do a research octane number. So this is going through doing a comprehensive evaluation. It is doing an optimization of the thing. It's doing a whole series of experiments right now. It is building, when it's done, it is now building models in the format that is specific for the spectrometer, and it just wrote a report. It took 16 seconds. So that's the kind of thing that you can do with automated technology. And then what that does is that gives you the way of easily following a process over time. So this is just looking at different boiling points. And you can look at the model quality, you can look at model precision, you can look at the complexity of the model, and you can look at data quality. And all those things can be trended and are delivered to you automatically. So this is what the computer can do. So in the case of spectroscopy, the purpose is come up with a technology or utilize a technology that doesn't care what spectrometer it's using, doesn't care what software, chemometric software it's using, it just doesn't matter. The process of doing the optimization is identical. And this is a way that you can, basically, you can speed that process. You can update models basically instantly. And then from an acknowledgement standpoint, we've done a lot of work with a lot of different companies, and they've supplied us data, they've given us hints, they've given us criticism, and I'd just like to do a shout out to a bunch of the people that helped with this. And no endorsements here, it's just these are people that are good. And then, so the final thing is just the takeaways that you could walk out of this room with. Think about the narrow AI versus broad AI. Focus in on the things that are specific to an application. It's not going to be the same thing each time. Your opportunities are in sensors, they're in spectrometers, and they're in chromatographs. And you already have AI tools that are in use. They add value to the plant, and I recommend that you continue pushing them. So I think our industry is behind the times, certainly behind automotive technology, and there's no point in doing this. We've always led the field. We haven't followed. So, and I'm done.
Any questions for Brian?
See, I told you I could put him to sleep.
No? Okay, well, thank you, sir.
Okay.
Much appreciated.
Thank you.
That's the end of the first session this morning. I think we reconvene at 10:15 for the last session of the conference. 3 more papers to go. So I'm sure coffee is down in the exhibit hall. We'll see you all back in 45 minutes.
Test. All right, let's get this session going. This is the last session for the show. We'll begin the session 10 now. The first talk is going to be Matthew Long and Michael Koo. Matthew is currently working at Applied Analytics as a sales engineer. He went to school at the University of Massachusetts for chemical engineering, and he's worked at Dow, Sakia, and now Applied Analytics. His hobbies include both fishing and cooking. Michael, if you want to step up. Or Matthew, sorry.
Alrighty, thank you everyone so much for being able to come here. Appreciate you folks turning out. As was mentioned, my name is Matthew Long. I'm sorry, you guys can't see that. We don't want that. No. Yeah. Like I said, it wouldn't be. Slide. Where are we? Thank you. Excellent. Okay. All right. There we go. We got our obligatory technical difficulty out of the way for 2023. All right. So my name is Matthew Long. I'm a member of the sales team at Applied Analytics. We're a process analyzer company based out of Boston, Massachusetts, that primarily deals with UV vis spectrometers, infrared spectrometers, and the likes. However, I wanted to take the next few minutes, right, to briefly discuss some challenges that we've actually seen in sulfur recovery units when it comes to sample probes and the associated, so those challenges along with potential design solutions that ensure long-term success for both process analyzers as well as the sample conditioning system. Okay, right. So if you take a look up on the screen, you can have a sample sulfur recovery system, right? These units are employed to remove hydrogen sulfide from the gas stream and ultimately convert that to a less toxic form. I'm sure you folks are most aware of this, but for those who aren't, please bear with me. Hydrogen sulfide is an impurity that is often found in like crude oil, natural gas, and it's both corrosive, toxic, and needs to be both properly removed of and disposed of, right? So modern refineries opt to recover the sulfur in its elemental form by using the modified Klaus process. In this process, basically you're going to react sulfur dioxide with hydrogen sulfide, with the ultimate goal being to create elemental sulfur, right? So, again, moving left to right, you have an amine unit and stripper that work in sequence, and they're basically just going to go and to remove and concentrate that gas. The stripper's going to release that acid gas, and that concentrated acid gas, which can be very high % levels, is going to send through a Klaus unit. The Klaus unit typically is composed of like a furnace unit, so we're going to partially burn some of that hydrogen sulfide to SO2, and then there are catalytic beds which will go and convert that to elemental sulfur. And then lastly, you can have something like a Scott's process or incineration unit or whatever that you can do at the end to kind of fix that. Often there are unwanted species that are involved here that create headaches, like ammonia coming off the stripper, hydrocarbons from the amine breakdown. In general, it's a challenging process. It's a difficult process. If something goes wrong, it has the potential to make things painful very quickly. So for the purposes of this application, we're mostly going to be looking at stuff shown after like the amine unit, like at AT5 or AT8. We do have some other applications, and certainly if you want to, while that won't be the focus of this presentation, you can come afterwards and chat with me about that. Right. So for my visual people here, here's just the reaction that we care about: H2S plus SO2. Oh, that's funny. Plus SO2, and basically we're going to get that to convert that to elemental sulfur. Right. So. All right, okay, great. So what are our takeaways from this, right? Okay, so it's going to be hazardous, right? Hydrogen sulfide will kill a person exposed to minimum levels, right? At a couple hundred ppm, you can be unconscious. If you get a whiff of this at 1,000 ppm, you'll be essentially killed almost instantly. I always think it's interesting, when you go to school, folks always go and say, oh yeah, hydrogen sulfide smells like rotten eggs, does all of this, and they always neglect the fact of just how lethal that is, right? So really anything we do around that, needs to have process safety, safety at the forefront of everything. The next thing is corrosive, right? The streams that we're dealing with are corrosive, hence the name acid gas, right? If you have a corrosive material that's not rated to be in contact with these gases, you are setting yourself up to have a bad day in very short order. And I'm just gonna say it's a challenging process, it's a painful process. If something goes wrong, you have the potential to form solids like ammonia salts, elemental sulfur. A big thing that happens is the ammonia, for example, coming off the stripper. If you don't fully combust that, right, you have the potential to form ammonia salts later on. Elemental sulfur is another bane of process engineers' existence. And like I said, while that necessarily won't be the focus of this presentation, we do have some unique ways to deal with that, and you can certainly come and chat with me later about that. And this is again for my visual learners. Well, actually, that's my next slide. I apologize. 46 workplace deaths were caused by hydrogen sulfide exposure in the United States between 2011 and 2017. And quite frankly, in my opinion, there's no reason why that should be zero, right? Unfortunately, that's the world we live in. And if you go on the Occupational Safety and Health Administration's website, or OSHA, here in the United States, you have the opportunity to read about these accidents, and it's really quite tragic, right? Because there's often confusion about the streams. There's often confusion about the equipment, and very much preventable, right? So the gas is also, as I was mentioning earlier, it's hazardous to humans, even at low concentrations. There's also the potential for olfactory fatigue. Try saying that 10 times fast. But if you get to above like 100 ppm or so, you're not going to be able to smell it, right? And unless you have portable gas detector, if you are getting in a worse situation, you could be completely unaware of that until that's too late, right? It's heavier than air, so like I said, if you're in a confined space, that's going to present challenges. And it's flammable. We kind of take advantage of this fact to basically get it out of, get rid of our acid gas, but it's still flammable and something that we want to keep in mind, right? Okay, so here's a quick scenario that we go through in our paper. I think we have something like there's a 50% source of H2S, like point source that's released. And this is basically describing how quickly H2S levels can reach lethal levels 1 meter away from a diffusion point source. Obviously, this doesn't take into account factors such as it being like heavier than air, bulk diffusion, wind, air movements, right? But you get an idea of like how quickly things get bad for you. I'm not sure who the visual folks are in the world, but I'm a visual kind of guy. I like seeing that. It puts things into context. So you can basically see the first line of the graph, right? You're going to have, where that olfactory fatigue is going to set in. And then basically all these other lines on the graph are really positions that you do not want to find yourself in, right? Next up, corrosion. It's not a friendly process for your equipment. Depending where you are in the process, right, you have the potential for hydrogen sulfide, sulfur trioxide to be present in the process stream. The hydrogen sulfide, for example, it's, upon contact with water, it's going to dissociate, you're going to release a proton, form a bisulfide ion. That's going to have sort of a redox reaction within the steel. Sulfur trioxide, that can form as a side reaction in the Claus furnace, right? If you're overcombusting, right? And if you have moisture present, you're going to have the potential to form sulfuric acid. And you know, if you're below that acid dew point, you're essentially going to be having acid rain in your process equipment. And you know, needless to say that if you're not prepared for that, that's not going to be good for the ultimate longevity of your equipment, right? Okay, yeah. So, and this is just again, you know, for my visual folks here, we can just see basically the acid dew point temperature on the y-axis. We have the SO3 levels in parts per million on the x-axis. We have different different concentrations of moisture, and you can basically see, you know, kind of where those dew points will be. You know, just so you can put that in the back of your head. Okay, so I said I like to fish and I like to cook. So we're on to salt formation. So you know, I strongly, actually, as a side note, I strongly encourage anyone who likes fish and likes to cook, definitely go and do a salt dome on your fish. You'll get like an even cooking temperature, and it really tastes delicious. And so while you know, salt crusts may be delicious for cooking whole fish, the same does not hold true for process equipment, right? And like, here's the example you always see of, like, you know, in heat exchangers, they tend to foul and have salt formations and build up within the pipe. And, you know, we even come up with things about like fouling factors, and it's the bane of existence. And, you know, this is something that, you know, we want to avoid in the sample probe, if at all possible. Right, so like, you know, here's one of, you know, one of the graphs just talking about one of the ammonia salt formation temperatures. So basically, it's a semi-log plot. You have the partial pressures of, you know, ammonia and hydrogen sulfide on the one hand. You have temperature and Fahrenheit on the bottom. The blue line here, right, that's basically going to represent the line where ammonia salts are thermodynamically favored to form, right? So if we're above and to the left of that, it's going to be favored to form as a salt, and, you know, if we're below that and to the right, it's going to be disfavored, right? So anything that we have, we want to make sure that we're kind of away from that. You know, it's funny, as a side note, I work with some electrical engineers, and they always get angry at me and say, "Oh, you know, you chemical engineers, you know, your graphs never pass the function test," you know, because we have all those phase diagrams with different lines and whatnot. And so he's very pedantic like that. So made sure to limit all of that, right? Okay, all right. So great. So we've identified some of the key hazards that you'll see and face here, right? So what are we going to do for solutions, right? Right, and some of those key hazards include, like, you know, the material, process being corrosive, process being hazardous, and just, you know, just quite frankly difficult to deal with, right? Right. Well, how are we going to look to address that, right? Well, you know, for starters, we want to ensure that, you know, we want to try to ensure it doesn't foul. You know, in this case, we want to ensure that the probe is heated in such a way that, you know, the sample will remain heated, and we won't get the formations of, you know, solids and salts that we're talking about. You know, the next thing is we want to ensure that this is easily maintainable, right? We want a probe that is both easy to maintain and allows for plant employees to work on the probe if need be, and do so safely. Right, that needs to be at the core of everything. And if you have something that, you know, you can't work on or can't serve, right, that's going to present challenges down the road, right? You're pushing off the inevitable, right? And to add to that point, you know, we need to be able to isolate it from the hazardous, you know, process chemistry. Can't say it again. Hydrogen sulfide is toxic. And we want to isolate that. And lastly, it's called acid gas, right? We need something that'll hold up to that, right? The gas is literally called acid gas, right? So what have we done at Applied Analytics to help address this? Well, you know, we've developed our Pro 500 acid gas probe. in part to specifically meet some of these criteria, right? So it's a steam heated probe, right? And so this works to ensure that everything prevents fouling, prevents the formation of acid dew points. It's above the acid dew point. Next thing, it's a straightforward design, right? I've got a blowout kind of on the left to show you all the parts involved. And I always like to say when you're working and you have something, you want something so slick, so simple, so sleek, so elegant, right? That you're going to be confident in that. Like I said, there are isolation valves to ensure that you can isolate the process chemistry, from where the filter assemblies are. And this is essentially designed to be used in conjunction with an aspirator or pump, essentially to motivate flow and return that sample back to the tap point, right? If that's unclear, I have another slide another slide following this that'll show that more clearly. And kind of lastly, it's made with NACE compliant material, right? You have 316L stainless steel, right? That's going to work to be resistant to the acids. It has corrosion resistant FFKM O-rings. Okay, right. So here's a cutaway, right, of what I was showing to kind of give you a better idea of like what's going on with the belly of the beast, right? So starting at the pipe, the sample is drawn up through the probe. Sample passes through the isolation valves, through the probe body, and kind of on its way to the sample conditioning system and analyzer. Right. The aspirator driven return sample then moves back down through the tap point, right? And then looking back at the top of the probe here again, right? We have steam making its way from the left-hand side out to the right-hand side to ensure that we have adequately heated our sample, right? So to recap, right? Such a design, it's going to go and address the hazards associated with hydrogen sulfide by utilizing a simple and compartmentalized design, right? It's going to handle the corrosive nature of the gases involved by being specifically designed for that. And it's equipped to prevent the formations of solids or salts that could otherwise foul the equipment, right? And the hope is with all of this, right, all of these design features will ensure that your analyzer, your sample conditioning system, this will help extend the life of both of those, right? And I like to say hopefully keep the process engineers from getting too many gray hairs. This concludes my presentation. Thank you so much, everyone, for your time. Does anyone have any questions? And if not, I am the only person here at my company, so I do need to get back to my booth. So that's fine too. All right, thank you, everyone. Thank you.
All right, so our next speaker, I don't think needs much of an introduction, but we have Phil Harris. Phil Harris has his bachelor's in physics, his master's in chemistry. He is the president of Insight Analytical Solutions, and he has never met a whiskey he didn't like. So we're gonna switch out laptops here real quick, and then Phil will begin giving his presentation.
figure out some logistics here first. Yeah, thanks for the introduction, Greg. Oh, maybe I should have stuck to their laptop. Anyways, yeah, so thanks everybody for coming. So I'm going to talk a little bit about scoop probes, or single point sample entry return probes. I'll do this without a slide now, that's okay. So the issue that we're going to try to address, and there we go, we're going to talk about what's the scoop. The issue we're going to try to address with this is the fact that most extractive analyzers, most grab sampling stations, we'd like to have a fast loop there if we could. When we're looking at analytical measurements, we'd often like to get the sample there as quickly as possible, and especially if the analyzer or the grab sampling panel is a distance away from where we're going to do the measurement, we'd like to get high velocity flow rates over there. And so, you know, if we look at this, let me just see if my pen's working here. No, it's not. Okay. If you look at that figure in the bottom, you can see we have, you know, if we have a direction of flow, we have some differential pressure, and we've got a high pressure point and a low pressure point, it's pretty easy for us to get continuous flow through this loop. So I got this thing positioned okay. But it's going to require some differential pressure. And that usually means that we're either going to have process differential pressure available, or we're going to have to put something like a sample pump in, or we're going to put in a low pressure vent. We're going to vent to a flare header or maybe atmosphere. We'd like to find a way to be able to create fast loops without having to meet all those requirements. So like we said, many analyzers, many samplers don't require a lot of flow for them to operate, but we need flow in the fast loop in order to get a good response time. If you've been through the Tony Waters training or came to my class this week, you know, we talk about how the time delay in a system is the volume divided by the flow rate. So if we want to get fast response, we either have to keep our sample system volumes low, or we have to have a lot of flow. Fast loops will help to ensure that we get a fresh sample over to where we're going to do our measurement, and they often have to be engineered properly. If it's liquids, we often have to worry about pressure drops. If it's gases, we have to worry about compressibility. And so there's a lot of factors that can come into play when we're trying to figure out, well, how are we going to put a fast loop, or how are we going to design a fast loop for, say, a sampler. And there's a lot of issues and common problems that come up when we start to consider, how am I going to implement a fast loop at my facility? One of the common ones that we'll see is we only have one sample point. So we have a sample point to measure from, but we don't have a low pressure return point. So we have to try to figure out, where is that low pressure return going to go to? If we don't have a low pressure process point, now we've got to go, well, I can't return back to the same pressure, so maybe I'm going to need a pump. If we're going to return to a low pressure place like the flare header, we may be concerned about the volumes that we're going to put there. So one of the solutions which might come up fairly often is that we are going to, let me just see if I can pick up a pen here. There we go. Let's see if that works. One of the solutions which might come up fairly often is people will say, well, we'll just put in a pump. Sounds like a great idea. We'll just put in a pump. It's easy, right? Well, as soon as we put in a pump, we have a whole bunch of issues that can potentially arise with that. First of all, process pumps are going to be expensive. So we're going to have costs associated with the pump. We're going to probably have a lot more maintenance because pumps require maintenance. I frequently, when we're looking at analyzer installations, I say, I don't like to put pumps in because I make my analyzer mechanics become pump mechanics. They're fixing the pumps all the time. There's going to be a sizing issue. We had a meeting this week talking to some people, and they said, well, the problem was they oversized the pump, and it was cavitating on the inlet side. And so who's going to do the sizing for the pump? Did it get sized properly for my application? And then we also say, well, you know, it becomes this little bit of an engineering avalanche. We're going to put in a pump. Well, where are we going to put the pump? Well, we're going to pour a pad for it. Is there electricity where we're going to put the pump? No, we're going to actually do some civil. We're going to run electricity over there. Well, how are we going to know if the pump's overheating? Oh, we're going to put a temperature sensor in, and then we're going to bring that data back to see if the pump's overheating. What are we going to do if the pump fails? Oh, we'll do it twice. We'll put redundant ones in. And so we get into this little avalanche of costs and complexities in our analyzer installations. But wait, there's more. If we're running gas analyzers will often run at low pressures. You know, if we look at something like our gas chromatographs or an online spectrometer, UV vis spectrometer, they'll often be running near ambient pressures. And if our sample gas is at high pressures, if it's, say, a natural gas pipeline, I can't return process fluid back to the high pressure spot very easily. You know, it's tough pumping the gas back up to, say, 60 bar if I'm sampling from a high pressure natural gas pipeline. So it can be difficult to return to process. If I vent it to atmosphere, which a lot of fast loops will sometimes, these things are, if they're venting to atmosphere and I'm running natural gas, well, now I've got significant methane emissions. And of course, in these days, greenhouse gases, methane being anywhere from 25 to 40 times the greenhouse gas equivalent of CO2. If I've got a 5 liter a minute bypass venting to atmosphere, it's a significant amount of GHG emissions. If I'm taking it to my flare line, I've put an extra capacity into my flare. You know, if I've got a whole bunch of analyzers in the plant and they're all venting to the flare header, well, now all of a sudden my environmental guy goes, hey, can you guys put less stuff to my flare? And then yet another problem in a place where we often don't put a fast loop in, but we really need one, is near vaporizers. If we're putting a liquid vaporizer in near the sample tap, we would really like to have a fast loop in front of it, because vaporizers take very, very low liquid flow rates. So if you look at a vaporizer that's running about 1 liter a minute of gas on the gas phase side, it might only be vaporizing 2 or 3 milliliters a minute of liquids. And again, since time is volume divided by flow rate, what happens if we have very low flow rates on the inlet to the vaporizer, we can have very long time delays. Usually, if we have time delays in a liquid system that's using a vaporizer, the time delay is happening on this side of the system. And the problem is, if we're putting vaporizers out near the sample tap, well, we're near a process pipe where everything is one pressure. We have no low pressure return. And so these are going to run very, very slow on the inlet side. I think I do the calculations on a slide coming up, or I talk about the calculations on a slide coming up. But if that vapor is sitting on a 2-inch pipe nozzle that doesn't have a probe in it, you'll have about an hour or an hour and a half of time delay just to try to clear the pipe nozzle. Put a probe in, you might get it down to 20 minutes. But we're going to talk about a way to be able to do this a lot faster. So the way we're going to approach this is by going back, you know, I'm a physicist by trade. I go back right to the fundamentals of physics. Okay, let's talk about Bernoulli's principle. Bernoulli's principle tells us that when we have fluid flowing down a pipe, wherever the speed slows down, the pressure increases. And whenever the speed increases, the pressure drops. And this all comes out of kind of Bernoulli's equation. What this ends up meaning is that if we flow towards a cylindrical object like my pen, where the fluid hits the front surface of it, the pressure is higher. As the fluid shears around the object, all the fluid that normally would have liked to stay flowing in a straight line has to go around that object now. So it actually accelerates as it goes around the sides. And what we end up with is low pressure spots on either side of this. This principle has been applied by a bunch of people. There's ExxonMobil patents that have talked about this sort of an idea. Shell has looked at this for LNG vaporization in a system that's sort of like the one I kind of show at the bottom here. And you know, there's commonly been put in systems like this where if the direction of flow is coming in, they cut a probe angled towards the direction of flow. Now the flow impacts on that, drives its way up through that piece of tubing, runs across. They have another probe cut at the opposite angle away from the direction of flow. it creates a low pressure zone, and now you can get continuous flow through that loop and vaporize that flow. Gives you faster response at the vaporizer. However, it may not be the best use of the energy and the capacity of that pipe to actually generate differential pressure and flow. So we're going to talk a bit about how we can optimize a system like this. So again, if I am flowing around a cylinder, if my direction of flow is going this way, oops, I just triggered my video before I wanted to. Oh well, we'll watch the video then. So the bottom video is a mathematical simulation of flow in a pipe. And you can see what happens is as the flow increases, the red zones are where there's building up low pressures on the side. There's a little blue spot right at the front, in front of that probe, which is actually a low pressure zone. And then you see the Kalman vortices forming. This is the things that cause flow, probe resonance. And then they slow the flow back down again. It's kind of a cool little video. YouTube has all sorts of great ones for flow around cylinders. The important things to get from is if you solve the Navier-Stokes equation, if you do computational fluid dynamics, what you find is the high pressure region is out in the front of the probe, and the lowest pressure regions are on either side of the probe or that cylindrical object that's in the pipe. So how do we want to use that? Well, we kind of know flow likes to go from high pressure zones to low pressure zones. So if we could find a way to create flow between the front of that pipe and the sides of that pipe, we could use it to drive flow through a loop. So we'll talk a bit about how we do that. So I'm going to be using kind of this reddish colors to indicate where the higher pressures are, and blue to indicate where the lower pressures are. So what we start out with is a probe, and it has a mechanical insert in it, and part of that mechanical insert is a thing which we refer to as the scoop. And we call it a scoop because it looks an awful lot like a scoop. It looks like it'd be something I'd use to scoop dirt up. The unique thing here is there is a very optimal curvature to introduce in here, because what we want to happen at that scoop is we want fluid that's flowing along that's horizontal to flow around it and change direction by 90 degrees. So when people just cut it off at an angle and let it impact on an object, some of the pressure, the available delta P, the available energy that we could use for driving flow is being lost in the turn. So we did a whole bunch of computational fluid dynamics to try to say, how do we optimize what happens within this region? And I kind of drew that a lot more crudely here. This is what happens when my mechanical engineer does it. This is what happens when a nerd like me sits down with PowerPoint and says, I need to make something that kind of looks like that. But you get the idea. We're going to go around that corner. So what happens is if flow is coming in towards this, we build up a high pressure zone right in front of there. That is going to push fluid into there and have it turn around that 90-degree turn and start wanting to flow up. We attach a central tube onto there, and that way we can take our sample and allow it to flow up that central tube. At the same time as fluid is flowing and impacting on this probe, there's low pressure regions on the side. So we said over here on the sides of the tube, there's going to be a low pressure region. So we make a big set of ports on either side of the probe body, and those become our return points. Fluid that's gone up through the center region, let me just pick a different color here. Fluid that's gone up through the center region returns back through this annular region and goes out those ports and returns back into the process lines. So we put large ports on the sides, lots of surface area, and there's a place for the fluid to escape back into the process. And so by optimizing that inlet scoop and those positioning and shape of those side ports, we can basically increase by about a factor of 2 how effectively we can use the differential pressure that's available to drive flow through that fast loop we talked about. So by fast loop, what I mean is it ends up looking kind of like this. We have that probe sitting there. It's driving flow out the central region, returning back flow into the annulus. And what we do is make that into a loop. Run some tubing around it. You preferentially use fairly large bores so they don't have much pressure drop. So this creates a fast loop that allows us to extract from the process pipe and return back into the process pipe while at the same pressure. There's effectively no difference in pressure. There's a few kPa, but it's enough to continuously drive a loop through there. One port of entry. We can even include a little bit of sample conditioning in there. We can put a bypass line of a filter there. Or we can put an inline sensor in there like a Raman probe or an NIR cell or an oxygen probe or a pH probe. So if you've got a water application, you say, I'd like to have a pH probe that I can actually maintain. I could put a probe like this in, put isolation valves on either side of the return side, nice big bore ball valves or gate valves. Again, I don't want flow restrictions. And then I just have it flow over my pH probe. The limitations that we have to consider with this is physics is going to determine how much differential we can actually create. Hopefully this animation is going to go. Let's see. There you go. So there's actually a computational fluid dynamics simulation of this probe in operation. Fluid flowing along the pipeline. So you can see the vortices that kind of show up around on the back side, but it drives flow up the center side, returns stuff back on the return side, and back into the process pipe. So how do we apply this? What's good about it? In gas phase applications, they work really, really well. We have no issues with priming because gases are compressible. And so for gas phase applications, we can put this into any line that has a high velocity gas flow. It's going to drive flow up through the center region. We might use that to drive past a filter. But again, it could be driving through something like flow cell for a Raman analyzer. Could be driving through the flow cell for a near infrared or an infrared analyzer. It could be a hydrocarbon dew point analyzer sitting there. We can use it to drive continuous flow. And all of the flow gets returned to the process, even if it's at high pressure. So if we have a stream that has, say, H2S in it or methane we don't want to release, it lets us return back at pressure. In a typical example, if I've got about 10 meters per second of flow, which is a typical natural gas pipeline, if I got 10 meters per second of velocity of my pipeline, I will end up, and I put in 150 feet of 3/8-inch tubing to run my fast loop over, and I'm at 45 bar in that pipeline, typical natural gas pipeline, 600, 650 pounds. I'll drive through that loop at about 1 meter a second. So I get 30-second response time. This goes completely against everything I've ever taught all of you in a sample conditioning class, where I've said, if you've got a high pressure gas, the first thing you want to do is put a regulator in to lower the pressure. We're actually saying we're going to build this fast loop at high pressure. It goes completely against everything we talk about in our sample conditioning classes, where we say if you want fast response time, go with really narrow diameter tubing. This loop will run faster if I put larger diameter tubing in because the tubing contributes less pressure drop then. But it allows me to create a fast loop that will continuously run and return to process. Liquids applications become more challenging. They're challenging because we don't generate a lot of differential pressure with these. Liquid velocities in pipelines are usually fairly slow, 2-3 meters a second. At 2 meters a second of process flow, if we have something that has around the density of water, we'll only generate 400 millimeters of water differential pressure. Equivalent of 400 millimeters a head. This is about a pound. We can't get over a lot of hydrostatic head. If you talk to people who put scoop probes in or flow impact probes on liquids applications, they'll say, we tried it and it didn't work. And it doesn't work if you don't install it properly. If you put that probe in vertically on the top of the pipe, The differential pressure has to overcome the hydrostatic head. If the line runs up towards the analyzer, it will never prime. To do these installations, we have to try to make sure that the probe is installed on the side of the pipe, and ideally the analyzer is lower than it. So we have a downhill run for liquids that will self-prime. Otherwise, we've got to put a mechanism for priming in. So when we do the installations for liquids, our ideal installation is to sample off the side of the pipe and ideally have the analyzer be lower down, so that, or the composite sampler, the grab sampler, whatever it is. Otherwise, we're going to have to consider how are we going to get that thing to prime. Once it starts to flow, it's a siphon and it just keeps on going. But we may have to add a mechanism for priming if we're going to try to run uphill. So one of the great applications for this is things like vaporizers. We see a lot of vaporizing regulators get installed in a petrochemical facility, and you'll go into a plant, you'll be walking along, and there's a vaporizer, and it's somewhere up there in the pipe rack. And you go, how do you guys maintain that? Oh, we don't. We never go up there. How do you know it's hot? We don't. We run steam to it. How's your steam traps? I don't know. I haven't checked. Steam is one of two temperatures. It is really, really, really hot, or it's cold. Depends on how your steam traps are. And so, so when we have vaporizers up there, and if they're coming right off of a pipe nozzle like this, they can have a lot of time delay before we get into the vaporizer. And they can have really slow response times. So like I said, went through the calculations. On a 2-inch pipe nozzle without a probe, you probably have an hour of time delay getting into the vaporizer. If you add a probe that's about 1 foot long of 1/2-inch SCAD 80 pipe, you might be down to 15 minutes. Big time delays up there. These vaporizers only run at a few milliliters a minute. We can put in something like a scoop probe, horizontal on that same upper pipe run. Run 2 pieces of 1/2-inch tubing down. Put that vaporizer down at grade now. Put that vaporizer someplace where there's a platform where a guy can stand on it and actually do maintenance on it. And all of a sudden, we can get that fast loop going. It's going to be running somewhere between 1/2 meter a second or so. If I got 10 meters of lines, that might be only 5 minutes or 5 seconds to get down to where that vaporizer is. Now I have a fast loop in front of the vaporizer, continually have fresh sample there, and I end up taking that 15 minutes or hour response time down into the 30 seconds or a minute kind of range. Similarly, it doesn't have to be a vaporizer down here. Again, it could be a Raman analyzer cell, an infrared analyzer cell. I could have taken my flow cell for an infrared analyzer, run fiber optics over to it, and done an analysis that way. So here's one actually, it's not my favorite installation, because these guys put it right in on the elbow of a pipe. But this is an NGL pipeline, and they put the probe into the side of the pipe. They're running a fast loop out. The fast loop is running over here, running over to a JP3 infrared analyzer, comes straight out of the JP3 infrared analyzer, goes right back into the pipe. So now they have continuous flow through that flow cell, and it's being driven just by the velocity in the pipeline. So I'm wrapping up here right away. Scoop probe applications and advantages. In the gas phase, they can return a fast loop directly to, and I should have probably put into a high pressure process. So we can mitigate environmental emissions and flare emissions. So we don't have as much environmental emissions, we have less flow going to the flare lines. We can use the same thing for grab sampling stations like composite samplers. So in natural gas and CO2 pipeline analyzers, we can make sure that all of our fast loops are returned to the process. We don't have an environmental, greenhouse gas emissions. For liquid fast loops, we've used these for grab samplers and for composite samplers. Fast loops to vaporizers is a great application because it gets around all that time delay on the front side. And then fast loops to any kind of inline analyzer. Raman, NIR, FTNIR, pH probes, inline oxygen probes, inline dew point analyzers. We were talking with the Kiko guys, they do a membrane extraction, put that membrane structure in a continuous fast loop. So that's it. That wraps me up. If there's any questions, I'd be happy to address them.
So normally we put the sample probes in with the bevel in reverse direction for filtering. What do particulates do to this, and have you looked at any type of loading?
Yep, yeah, so that's certainly potentially one of the issues. If you've got so the question is that, normally we've always said, hey, you're gonna cut the angle of the flow of a pipe away from the direction of flow, at least in gas phase systems, because we're gonna pick up less particulate. And certainly that's true. We're gonna potentially pick up more particulate with this. Again, the nice thing is though, is we get to go with fairly large diameters through this whole thing. We typically run 1/2 inch, 3/4 inch tubing, so it's gonna be less likely to plug off that way. It could be problematic in a high particulate stream. Yeah. We have used it though on things like, used it on composite samplers for crude oil. So crude oil is usually, of course, got some sand, some water cut, asphaltenes, things like that in it. Any other question? Yes, sir.
Would you be able to use this as well, gas phase, in quite low pressures? I'm thinking of applications where you might have a toxic gas that you wouldn't want to have to handle once you've measured it. So a kind of a closed loop toxic, but at quite low sample pressures.
Yeah, it's really what drives flow through the system is, actually, let me put this 2 ways. So the answer is yes. So we've used it on flares, which are running at atmospheric. You don't get as much differential pressure, but it doesn't take as much work, because the pressure you get is basically rho, the density of the fluid, times the velocity of the fluid squared. So as long as you've got velocity, you're gonna drive flow through that loop. And you'll return into that same loop. So the answer is yes. Cool. Nobody else? Anything else? We got a booth inside, and we're happy to address any questions. Guess that gal's gonna come and swap back to the other computer. Thank you.
Phil, the microphone. We're going to do a little switching of the laptop here, so give us a few seconds. But our next speaker will be Edward Orr and Henry Lynn. Ed was an application specialist for NIR Systems, worked for a flow cytometry startup, and then has spent the last 20 years at ABB. He has his PhD from K-State and enjoys hiking, biking, and swimming. So once we get this laptop up and running, which I think we are, we will get going.
Thanks for sticking around for the last talk of the last day. I appreciate it. The presentation today is going to be low-level gas analysis in industrial settings. There's two applications I'd like to talk about. One is air monitoring, specifically in a clean room, but air is air. And the other one is an olefins process. So I'll present an overview of off-axis integrated cavity output spectrometry, or let's just call it ICOS, because too much of a mouthful to say all of that every time. Then we'll look at ethylene contamination monitoring and clean room air monitoring and draw conclusions. I gave a talk yesterday. For those of you who are in it, thank you for coming back, but this is the same slide you saw yesterday. There's only 2 repeat slides, but basically we bring light in from a laser. It bleeds through the back of a parabolic mirror. It bounces off the mirror several times. We get kilometers of path length. And as it's bouncing off of the mirrors, the back mirror, there's a detector, optics, it goes onto a detector, and some of that light's bleeding through. So we're collecting the sample as the laser is bouncing back and forth through the cell. We scan this laser, excuse me, I hit the wrong button. We scan the laser continuously. There's no stopping it. We'll pulse it sometimes, but we scan it so we can collect an entire spectrum. Now the spectrum's only going to be a nanometer, 2 nanometer spectral region, but you're looking at the fine structure of an absorption band, and this permits multiple components, if they appear in the same spectral region, multiple components to be measured at the same time. The off-axis design makes it very simple to integrate more than one laser and then pulse between the 2. So if you can measure, in one example, HCl and HF with one laser, you can slap in a second laser and measure ammonia. It has that capabilities. The other really nice thing about this parabolic optical arrangement, it keeps the light aligned, so to speak. So it brings some rigidness to a slightly vibrational area, you know, what you would expect to find in a process environment. Makes it a very robust alignment. We make these measurements at reduced pressure. We bring in low pressure to the analyzer, use orifices and a pump to maintain a very consistent low pressure in the gas cell. This helps sharpen the peaks, sharpens the bands. You don't suffer from as much band broadening. And then since we're collecting the spectrum, we can bring it into a chemometrics routine. And something to remember, these are near-infrared lasers. Whenever you're talking near-infrared spectroscopy, I don't care if it's a spectrometer or a laser-based technology, with chemometrics, fundamentally, and I know I'm going to get a lecture after I say this, but fundamentally, you're taking a nonlinear response and forcing it to a linear curve. And what PLS brings to the table is maybe an expanded range over a standard y equals mx plus b. But the other thing it brings to the table is you can trend beyond the range of the analyzer calibration. It may not be very accurate, but it's good enough to see increases and decreases reliably for process control. We do use the cavity ring down effect as a diagnostic tool, and obviously this technology has the power, if you have the logarithms, to update your effective path length in real time by looking at a piece of baseline, measuring the cavity ring down time, and that's directly related to the path length. So we scan a spectrum. Let me see if I can get it right this time. I'm going to click on the pen. Can you guys see this on the screen? My cursor? No? Okay. I'm kind of I'm old. I don't, you know, these all came out after I graduated college, but we scan the spectrum and you get a peak, right? This is fundamentals. This isn't a real sample. And you build a calibration over a spectral region that incorporates that absorption and any interferences that would impact that. And when the laser gets pulsed off, you can measure the ring down time as a diagnostic tool. So we're collecting this entire spectrum, albeit over a very narrow region, and using the ring down time as a diagnostic. Obviously, we convert this from transmittance to absorbance, so the peaks go up, which is a little bit more preferred. And here's an example of acetylene in ethylene. And you can see the acetylene band right here. And this is in nitrogen, so it's pure. And you can see one of the ethylene bands, that's overlapping. I mean, there's no question about it. There's a shoulder right here, a little red trace. That's tremendous overlap. And what PLS allows you, or not PLS, excuse me, what using a chemometrics routine does is allows you to get a little bit better LODs than just using Beer's Law. So if we look at how this is done online, or what kind of results you can achieve, if we take a look at the output of the final tail bed in an acetylene reactor in an olefin plant, where we have a pure component. Am I okay? Yeah, thank you, I appreciate it. Oh, good. I'm computer illiterate. So we'll present collecting data at the output of a acetylene reactor. This device gives us acetylene at an LOD of 2 part per billion with a sensitivity of 1.3. We define our LOD and our sensitivity as 2 or 3 times, depending which one, the zero gas baseline noise. And we could measure ammonia and water at the same time. Why is this important? For minimizing the amount of acetylene helps preserve a catalyst downstream. So as the ethylene shifts downstream for further production, it's a catalytic reaction. The acetylene is a poison. So they want to get it as low as possible, and they want to maintain it. If the acetylene spikes, they want a quick response to divert that, either to put it back through, or to flare it, or to store it, I don't know, whatever the engineers do. And the other really important thing here is minimizing that acetylene has a significant impact on startup time. The faster you can measure it, the quicker you can start up a unit following a shutdown. So with acetylene, the analyzer has a refresh rate of 10 seconds. There's a T90 involved there, and that would depend on, obviously, the volume of the sample handling system bringing the sample in. But the analyzer itself refreshes in 10 seconds. And here you can compare the time advantage compared to a very well-established technique, gas chromatograph, which everyone trusts. It's very accurate, it's very sensitive, it's a great analyzer. We make those too. So I don't want to trash GCs by any means, but you can see the time advantage here. We're talking seconds measurement versus a few minutes. And if these spikes are real, and they are, you get more reaction time to respond with a control move, whatever you're going to do. If you're going to divert it, you're going to flare it, whatever the engineers do. And this is the speed that an ICAS will bring, which is critically important in some cases. If we look at sensitivity, and this is all process data, this is not lab data, it's in the literature, it's referenced in the publication to go with this. If we look at sensitivity here, we're looking at about 60 part per million acetylene in ethylene. You're looking at a sensitivity of about 1.5 part per billion. And remember, the range that we're calibrated over is 0 to 30. So here we can trend this. We can see the stability even though we're outside the calibration range, and that's one of the advantages of using partial least squares. As this drops down in acetylene value, down to about 10 part per million, we see a sensitivity or repeatability between measurements of about 1.1 part per billion, about 1 part per billion. As it continues to fall, we're down to less than 2 part per million, which is below the LOD. And I should back up here, and we define an LOD as the lowest level which you can guarantee a calibration will work, not the lowest level the analyzer can see something. And there's a huge difference in those two concepts. But we're down below what the manufactured specifications for the LOD, and we have a sensitivity of 0.7 part per billion. And I feel a little bit stupid right now. Can you take my word for it that I mislabeled this graph? And I feel bad about this, but the axes were so small that I cut them off the diagram, and I inserted a text box, and I put in CO2. And I apologize. This is H2S of a GC versus an ICOS. Just looking at the accuracy, so the time scale is shifted so that the times match up side by side. And you can clearly see the accuracy of the ICOS compared to a very well-established GC technique that nobody would question. And so we have a technology that's extremely fast, very, very low levels, that's very accurate relative to established techniques that can be deployed in an olefins unit as a catalytic preserver, I guess, for the polyethylene unit. And it's very unique in the marketplace. The other application is clean room air monitoring. I spent years working in this industry, and part per million levels of pneumonia in clean room air. And we can do this in outside air too. It's air is air. But just trace amounts that you wouldn't even know was in the air will corrode a wafer. And what we're looking at here circled is corrosion on the trench wall, or the top of the trench wall, on a semiconductor wafer. It's a silicon wafer. And the normal is this ASTM graph, or photograph, I guess you'd call it, right here. And you can see the shape of that top. Trace amounts of ammonia get in there, and you can see the corrosion effect. It destroys this nice angle right here. And if that angle's destroyed, the wafer fails. The semiconductor chip, when you're done, you cut out the dies, simply will not work properly, and it causes a lot of scrap. This is called T-top corrosion. It's a huge issue. And it results from just trace amounts of ammonia. HCl and HF have other corrosion impacts as well at very low levels, not to mention the safety impact of having HCl and HF leaks. But we're talking measuring low part per million levels. So when we developed this, working with a customer in Asia, you know, the question we always ask is, how low do you need to go? And the answer was as low as possible. The same customer lost 8 people a few years back to an HF leak. HF, ammonia, HCl are used throughout a semiconductor manufacturing facility, so a great deal of research and a great deal of care is given to making these measurements. So we have a safety and a product corrosion impact we have to look out for. So if you're in a clean room and you're measuring various points, what happens if you see a leak? Well, if you see it before it's a problem, they can flood the room with clean air, dilute it down to levels where it's not traceable, and everything's good. When they do the dilution, if it does not respond, if you don't see the levels come down, then you have a big problem causing a shutdown and potentially evacuation of the fab. Graphically, this is in kind of a diagram of what happens. Clean air comes into a clean room. This is the fab, this is the sub-fab, this is isolated huge chamber where people work and all the equipment is. And it mixes with contaminated air, and it comes out all the various vents into the air. to help dilute out these components. And the sampling is done at hundreds of points throughout a fab, in cabinets, in rooms, many, many different points. And the idea here is as soon as the increase in HF, ammonia, or HCl is seen, they can pump in more air, bring it down to untraceable levels, and they know everything's okay. And of course, if it doesn't come down, then they simply shut down the unit for obvious reasons. So this is field results from the customer that employs this, and they were claiming lower detection limits of ammonia at 0.3 part per billion, HF at 0.1 part per billion. Precisions for ammonia 0.1 and HF 0.025. So they ran their tests and they saw the kind of data they were looking for. And then they did response time testing, because in addition to knowing how much is there, how soon do you know it is critical. And this was all done in an environmental chamber, a lot of safety issues involved, but fundamentally they ramped up the ammonia concentration to a known value and then flooded the chamber with clean air and watched the analyzer decrease. And you can see a very quick response time here where the decrease in concentration took 87 seconds to go from 22 to 1.5 part per billion. Part per billion, yeah. That does not include the flooding time, but the point is here, that's very fast. If you compare this to the normal technique, which is like an ion chromatography, you're talking 20 minutes. So it's a huge time savings. And then they spiked in ammonia into the same chamber and just watched the increase time. And you can see that they saw an increase from about 1 part per billion to 32 part per billion in less than a minute. So they got the speed on the ammonia. For HF, and this is a huge challenge doing this in a chamber in a laboratory because it's HF gas. But they bled some HF gas into this chamber and then flooded the chamber as quick as they could with air. And of course, the exhaust of the chamber was all scrubbed, whatever. But they saw a decrease from 16 part per billion down to 1 part per billion in 1 minute. So the response time, again, not only for the acetylene, but for air monitoring for safety and personnel reasons, it's the response time and the accuracy at low levels. It doesn't even matter, honestly, how accurate this is. What really matters is, hey, we see it increasing and we want to stop it. So what do? You need that advanced notification. And when it comes to HF, you know, there's people involved. And you want to know if it's climbing right away. We do a lot of this in semiconductor, and it's a well-established and well-received technique. And I'm going to go short today, but you're probably happy for that because lunch is served. So basically what we bring to the table, or what off-axis cavity output spectrometry brings to the table, is a very fast measurement. And gas processes, air monitoring, where very low levels are required, and you need the result quickly to make a move, whether it's a control move or environmental safety compliance issue. You need that speed. That's what we're told. So we built an analyzer with that speed. Very low limits of detection. Extremely sensitive, so if you see a change, you know it's real. And we can go to these levels because we're combining multiple factors. A very, very long path length, kilometers, very low pressure, nice sharp peaks, chemometrics to help account for any remaining overlap. You will never remove all the overlap in some of these things. You have to account for it, so you regress about it with a chemometric technique. Operating outside of its calibration range, we'll do that. It won't be as accurate. You have to question the absolute value of the number, but the trend is real due to the sensitivity. So that at the end of the day, what ICOS brings to industrial applications, it enables, I guess would be a better term, it will enable effective process control in fast-moving processes or in critical environments where early detection is very important, like safety monitoring. On that, Paul, I'm sorry, I talked way too fast. Are there any questions? Yeah, okay. Oh, and by the way, I'm staying neutral, but you can find me if you want to guess where I might be if you have any questions. Not talking about the actual product, though, just the technology behind it. No questions? Oh, that's good. Thank you very much. By the way, this is the first time this conference ever spoke at this conference, and I have to say I like that they're not sales talks. I know we all do to a degree, but I like that format a lot. Thank you.
Well, that's the end of our technical presentations for the conference. Lunch will be downstairs in the exhibit hall. It's not the end. After lunch, we have a panel session up here discussing the latest trends in regulatory affairs that affects our industry. So we'll have a couple of experts talking about what's coming down from the EPA and Texas regulators, TCEQ, the new TDLR requirements for buildings, codes, and stuff like that. So please come back for that. I think there's some things to be learned from that discussion. And then at the end of that, we'll have wrap-up presentation of the Best Paper Award, closing remarks. And then tomorrow we have hands-on training. I think there are 8 or 9 vendors who have equipment here. Training slots are still open. And scorecards. Yes, if you have a scorecard, please put it on the table by the door or the back so that I can tabulate and let the magic work its process. Thanks all for coming, and we'll see you after lunch.
are going to be good, and the microphones are open. I'm going to chit-chat for just a little bit, and I'm not here to introduce a topic or to teach you all about it and explain it. I literally have one slide, and that one slide will hit on a couple of key topics, maybe spur your interest in something, and then y'all can ask. We can dialogue about whatever you may want to dialogue about. It is true, I've been coming here for quite some time, back to the days of meeting at the Monument Inn, and smaller groups back then for those of you here in the Houston area chapter. But we've been talking about flares mostly during my time with ISA, with you guys here at ATC, but touching on other things lately too. Naturally, when Wes said talk about future rules, I am no good at prognosticating the future, just like you. It seems that we're constantly being surprised at what comes out of the agencies. We kind of have a flavor for what's coming next, but you never know really what it's going to look like. And just the last 2 weeks have been an absolute flurry of activity, and much of it is analytical measurements in nature, so that should make all of the vendors in the big hall very happy. There's a lot of new stuff coming our way. So I'm going to throw all of my 4 topics up on the slide all at once, and I'm just going to talk through them really quickly, and when we have the Q&A part, y'all can feel free to go down whatever path you want to go down. So I'm going to focus just on air because most of the rules are touching on air, but I'm going to give a disclaimer. Those of you who are in the petroleum marketplace, please, hopefully you're reading up on some of the things going on. The water world is going crazy, and there are tons of community, local POTW, wastewater treatment systems really having huge scrutiny over refinery and petroleum wastewater emissions. Those rules have not been updated in a very long time. So there's a lot of community monitoring going on relating to wastewater, and that is resulting in a lot of activity at the agency looking at new and expanded rules for the refinery sector in particular, those categorical standards. So you're already under the microscope, and some of those 200-year-old analyzer systems that are still in wastewater service, you may want to consider giving them a revamp. But I'm going to talk about mostly air, and the 3 things, it's funny how they all kind of have a common first letter. It's formaldehyde, flares, and fence line. And we've been talking about those 3 Fs for a long time, and it's amazing how they are persistent. They are constantly coming up in all the new rules. So just a reminder, some of you have cogen units in your sites and your plants. Those cogen units, those gas turbines, one could spend a day talking about the history of this rule, and it's got a very bad letter system. The rule is called MACT, and it's subpart YY. There's 4 Ys, and you just kind of go, why is this rule just dragging out literally for decades? So this subpart Y rule is no longer been stayed. It is now active, and as it's being active, gas turbines have to monitor for formaldehyde. Magic number is 91 part per billion. But the 91 part per billion on the discharge limit is in a very high gas flow, right? The exhaust stream flow rate. So if you say, I have 90 parts per billion, so I'm below the limit, if you take 90 part per billion times that massive flow rate coming off of your stack at your gas turbine, you are going to trigger major source threshold for permitting for that one stack. So the goal is to find an analyzer that can get you very low detection limits for formaldehyde and not report 90, but if possible, try to report a lot lower. So we've been involved within the last year. Spectrum's analyzers have been involved with about 160 gas turbines throughout the country. Our average detection limit using our long path FTIR is about 15 parts per billion, and that's in a gas turbine exhaust. That's the average. Our best ever is around 6 ppb. And we had a few gas turbines fail the test, require some tune-up and some other things, and then we get to get called back out and test again. So this is a pretty big issue for formaldehyde. We're well into the testing period. Like we're obviously the rule came out effective last year. So we're a year into it. We've done about 160. There's a very small world of analyzers able to do this test. And a lot of the traditional FTIR devices are not able to. They have too small of a path length. So just be aware that that's out there if you have a gas turbine on your site. This rule is kind of hidden, but it's making the news because formaldehyde is a hazardous air pollutant. And people are now taking notice of these rather large numbers that people are measuring. Small numbers in the measurement, large numbers of formaldehyde in the aggregate, if that makes sense. The second thing I wanted to touch on is maybe a rule that we've been talking about for a long time. That's the ethylene MACT. The ethylene MACT came out 3 years ago after the refinery MACT. So the first rule was refinery MACT. Then the ethylene sector MACT came out. That rule affects about maybe 97 or so flares in the ethylene sector. This rule has been working its way through the timetable, and lo and behold, we're just like 6 weeks away from the magic date, the effective date. So hopefully, everybody that has an ethylene cracker, ethylene flare has already put in their flow meters, their analyzers, whatever the calorimeter, GC, mass spec, whatever they've selected. Hopefully those are in place and ready to go. I say that kind of tongue-in-cheek because we've reviewed, looked at probably 70, 75% of all of those ethylene flares within the country. And of those flares, most of them still have yet instrumentation to go. Oh, this is not up?
It's not up.
All this time I'm talking and nobody. Start over.
No, just. This is what's second. This is what's showing.
Oh, look at there.
Sorry. My fault.
Y'all don't have to read fast. There's only one slide. So this might help a little bit. So second item was ethylene MACT, the miscellaneous organic NESHAP, and the organic liquids distribution MACT. Those MACTs all come due here in 6 weeks. Hopefully everybody's caught up to date and is ready to go for that. So if you remember, the last time I've been here talking, the flare section for refineries covered about 510 or so, 513 flares. This ethylene rule covered about 97 flares. So if you're in the flow meter business, ultrasonic flow meter business, or if you're in the calorimeter, mass spec, GC world, that's a lot of flares to play with. So hopefully everyone's enjoyed this run of support for these sites. What you need to know of what's new are the next 2 items. So number 3 is the flare reconsideration came out about maybe 10 days ago. That reconsideration is absolutely turning the flare world upside down. And you may or may not be tangentially acquainted with this little problem. It has to do with visible emissions, the smoke, time periods when smoke comes from the flare. The rule, as it was written several years ago under the new MACT, the refinery sector rule, basically allowed no startup shutdown malfunction events. The analyzers had to work at all times. You could not claim a power outage as an excuse for why the analyzer isn't working or anything else. It basically is the first rule we have ever got that allowed zero downtime. The rule allows zero downtime. The word downtime is not in the rule. So the analyzers are supposed to run on these flares continuously. But the smoke issue, y'all got about 3 excursions. You could have a smoking flare event. It could happen 3 times. The only thing they did is they kind of said that if it were a major force majeure, power outage, something outside of your control, a power outage didn't count towards those 3 smoking flare events in a 3-year period. So just last week, 2 weeks ago, they took that away. So all you got to do is think about what that means. We used to say, I had a smoking flare event because the compressor tripped, right? And I was smoking for 2.5 hours, but we got everything back online. I'm good now. But we use that as a excuse, the justification for why we had a smoking flare event. The rule now says those visible emissions are violations, not a deficiency, not an oops, not a you get one and I got to do a root cause analysis. You still got to do all that. But it now equals violation. And a violation, forget what inflation is now. Inflation makes it like $43,500 per violation per day. So if you have a smoking flare event now, it's violation on the day it happens. A smoking flare is now a violation. So when you go home, the number one thing people are calling us about are the little things called the cameras that stare at the flares and show the video in the control room. People put in these flare monitoring cameras and recording systems, and we all kind of care about them a whole lot. It's just a recording, and we save the data back on a server somewhere. Now everybody wants to know the second smoke started to appear, the second smoke stops, how long was I really smoking for, and how can we mitigate that? How can we readjust our available steam? A lot of control things going on. So just when you thought your flare situation was done, signed, sealed, and delivered, this reconsideration is really shaking up the visible emissions world. So more questions on that, we can chat about it again later. By the way, it's retroactive, so it goes back to the refinery rule and the ethylene rule and all MACT standards coming forward. And speaking of new MACT, this is the other huge thing that came out, 444 pages of little light reading for you if you don't know what to do on your airplane ride home. Pick this thing up and give it a gander. It is not a rule only for the hazardous organic niche app, that is these few chemical plants. This rule actually is very broad. It touches on 6 different niche apps and 4 new source performance standards. So we call it the chemical sector because it's not just the HON. It's actually several. It's polymers and resins 1, polymers and resins 2, and your environmental folks will know what rules you fall under. But it's just very broad for the refineries, for the chemical sector. We knew this type of rule was coming. I just wasn't expecting it to come this big, this heavy, this fast. So we think, and the EPA is not even certain how many flares this may affect. It could affect over 500 flares, but the way I count it, it's looking more like closer to 1,000. 1,000 flares in the various chemical sectors. And there's chemical plants in faraway places, right? They're not just Texas and Louisiana. There's a lot of chemical plants that have little flares. So all of these are now under the same instrumentation requirements, the same. There's no carve out. It's all of these, it's a lot of flares. That's a lot of analyzers. That's a lot of flow meters. That's a lot of engineering. A lot of shelter integrations are coming our way. The other thing that this chemical sector rule is giving us is a fence line monitoring requirement. This is a little different. This doesn't affect every single chemical plant. This is affecting about maybe 280 sites throughout the nation. And the fence line rule by itself is very complicated. It addresses 6 compounds of concern, those 6 compounds being benzene butadiene, ethylene dichloride, vinyl chloride monomer, chloroprene, and ethylene oxide. So if you use or produce, it's the using part that people are getting sucked into this, right? If you use or otherwise produce any of those 6 compounds, you're in. And the EPA has record of at least 286 locations to which this part of the rule is going to apply. And I know this group, I mean, I've been coming here for a long time. We tend to focus mostly on process analytics and process analyzers and things like that. Not so much on ambient air monitoring. There's other conferences one can go to for that. But I was kind of curious if maybe next year we not do maybe a Monday workshop on ambient air monitoring and get some of the other vendors who have unique applications in ambient air. Maybe we do a little workshop and get a couple of vendors together. If you think that would be good, and if the leadership committee likes it, maybe we could do that on a Monday. Put that on your comment sheet or something. Yes, that's a great idea, or no, let's stick to process analyzers. But if you think it is, it could be fun, and there's going to be a lot of people talking about this. The last thing I wanted to say was chloroprene really addresses only one facility in Louisiana, so all the other ones are really what we're talking about, the benzene, butadiene, the PVC plastics world, right? PVC, EDC, and VCM, and then ethylene oxide. So I'm going to stop there and leave it open for any of those paths. Whatever path you want to go down, your questions are on. Happy to take your questions. And I don't know if we're going to do questions now, or do you want to do questions after the group?
Wait until after we hear everybody.
Hear from everybody. All right. Okay. See, one slide. I didn't lie.
The next person that we're going to have is James Dorsey. And James works for Siemens. He's the GC Director of Strategy. Previously GCI Operations Manager, 40 plus years in process automation and analytics. Has worked around the globe on various projects and is currently living in the Hill Country, or as we call it, God's Country. Yeah, that's what it is. Hunting and other, and if you are nice enough to him, he'll show you pictures of the huge deers he's gotten.
Thanks, Wes. Thanks. So, will this just jump to the next? Getting that up. While I'll mainly address the IBC for the U.S., it does apply beyond the U.S. as well. So there's a lot of other countries and manufacturers or facilities as well that reference the IBC. But there's not only the IBC, there's many other codes that we need to address as we go through things. Now, as we all know, with analyzers, they need to be integrated into some form or fashion for various reasons. So as we do that, what applies, what moves through that? So I have a few slides here, but
this is what you see, this is what's coming.
Okay, great, thank you. For us to address, one of the things to note is the regulations and the codes are updated every 3 years, and states are required to adopt what's been published within a certain period of time. Now, they're not always on time with that. They're not always up to date with that. They don't stay current with it as often as they should. So, and we'll talk a little bit about that here in a minute. But in the IBC family of codes, there's 15 family codes that are updated every 3 years. Now, for our industry, pretty much, there's only a handful of them that would really apply to us, but there's others that could apply as you move through that. But keep in mind that not all the states adopt IBC. There's still some states that let each local agency do their own thing. So that's why I listed some of the codes down here at the bottom, which those 3 codes, the standard codes, the uniform building codes, they are the ones that built the IBC that we really, first edition was in 2000 when it was being adopted. But everybody has pretty much migrated to adopting some form of the IBC codes. But for the IBC itself, that's for the building portion of it. And it doesn't matter if we call it a building, a shelter, or an enclosure. If you shut the door behind yourself, it falls within the code. Okay? But Significant changes is all I'm really going to address. There's a lot of changes within it, and I'm not going to go through all these changes because we wouldn't have time. Just between 2015 and the current code, so Texas, Louisiana was under the edition 2015. They've just recently adopted to move to IBC 2021. So they skipped 2018, going to 2021. There's 253 significant code changes that apply and how they're to be addressed. So just because they didn't adopt 2018 doesn't say, okay, we don't have to worry about 2018. It got covered when it was adopted in 2021 as well. So across the US, there's from 2006 to 2021 today, so various states at various levels of what they've adopted. And when I say they've adopted, it's a rule or it's a state law that these codes apply as a minimum. And it either applies to the owner or the manufacturers or a combination of. So that's with the IBC, and we'll talk a little bit about some of the changes here in a minute. The other piece is when we look at the codes that have been adopted, a lot of them from the environmental aspect of it, I shouldn't say environmental aspect of it, I guess more from a climate aspect of it, with heating and air conditioning and that type of stuff, would refer to the ASHRAE table. Well, the IECC refers to the ASHRAE tables of what you're to adhere to or to follow. And a lot of times they conflict. There's only about 7 states today that still reference IECC and or ASHRAE, or just ASHRAE. And in some cases, there's one state, they reference IEC 2018, and then they'll reference ASHRAE table 90.1 2010. Well, those conflict with each other now. So which one do you follow? So that becomes a debate. So most states have moved away from referring to the ASHRAE tables and just go to the IECC. In the ASHRAE tables as well, in the past 2 editions that were released, there's over 200 code changes in there and or adoptions that have been made. And they just released in January the 2022 edition. Okay, so we're probably not going to have to really worry about 2022. There's about 80 that are associated with it, but really you have to go back to what the state has adopted. The other thing to keep in mind is not only the code, but the state, what they've adopted, a lot of times they'll add amendments or rules to that. Okay, exempting something or changing something. That's rare. And unfortunately, within our industry, we don't get the coverage, or we don't get the lobbyists to help us in some of the areas that usually we were always way ahead of what was coming out here. But it covers a vast area, and we're just a fraction of, so they're not really willing to divide that up. Speaking with a lot of the state governments, we can get a little exception here or there, but at times we can get an exemption if there's another code like the NFPA or what have you. Because even like when we went into this with Texas, they say you will not have any more than X amount of CFM leakage through your building. Well, we pump 6 air changes minimum through our shelters. That was Greek to them. They finally understood it and where that's at, but they're regulating, okay, how much air conditioning, how much stuff you're doing. So it's an educational process a lot of times with the state agencies. And there are some state agencies, if you work with them, they will grant you exemptions in certain areas. Example, state of Ohio. If it's a pipeline cutting through the state, they'll say, okay, you don't have to fall under our program. You need to follow the rules, but you don't have to fall under our program. State of Wisconsin in the past, I've gotten exemptions from them in the past for certain things. So it all depends on who you're working with and how you work with them on it. But again, there's a lot of changes here, and I'll discuss mainly the significant rules that we're probably going to be facing here in a little bit. But as I mentioned, okay, here's a map of the IBC. And I just mentioned a minute ago that Texas is moving in September, effective September of this year, Texas will be IBC 2021. Louisiana has already moved to IBC 2021 effective January of this year. So whatever's in there now has to apply. We'll talk about the IECC in a minute. Those are the two main codes that we wind up having to follow moving through that. There's plus or minus, and everybody's trying to adopt new codes. And if you look out there and you go to like the IBC, and you'll see the map here, the map is not correct, and I state that. You really have to work with the state agency as far as what they've adopted, because some of the information you get from different agencies is not always accurate. So go to the state, they will tell you with what they're currently under and where it's at. But there's about 20 states over the past 12 months that have really migrated to move up. Most of them are at 2018. There's a handful, or about, I think it's 6 or 7 that have moved to 2021. And then with the IECC as well, Louisiana, effective July of this year, will be IEC 2021. So the rules following in that. But for Texas, again, it will be September of this year that will be actually enforced as far as law. They've already adopted it, it's moved, it's crossed through the House bill. So following those, as far as what do we have to do? So that's what I really want to spend a few minutes on is, okay, what's changing? What's happening with this? There's, building code requirements that are changing, and specifically with like the insulation in the roof of the shelters. The R value is increasing from R38 to R49. But more importantly, they've actually added a new piece within the codes that any firewall, and all shelters now, their outside walls are fire rated, must support 5 pounds per square foot. So it's going to have to support 5 pounds per square foot on a shelter wall, if there's a fire. Now, I don't recall and I don't remember exactly what it was as far as what the intensity and what the duration of that is, but those things are going to have to start applying now. And some are actually asking for higher fire rated walls in certain states. Some states it's 1 hour, some states they want 2-hour fire rated walls. And there's a number of ways to achieve that with, let's say, sheetrock, insulation, blown-in insulations with retardants in the insulation, coatings, paint, that type of stuff. So there's a lot of new products out now as well that you can actually achieve the fire ratings without as much. Texas is probably the most stringent state, along with the state of Washington. They will actually require you to be certified in the state of Texas, the manufacturers. It's not so much the end users of how they put their stuff together. And if they want to change something, they have to submit that to go through. So building manufacturers or even integrators of what they're changing and how they achieve that certification. It does move. So when you look at buying a project, one company may do it one way, another company may do it another way, but okay, they're certified. And those certifications have to be, renewed every year. So it's not just a one-time deal. And, or in the state of Texas, if they go too long without building a project, they actually have to go through another formal certification process. So that can take place. Now, not all agencies are as tough as Texas. They have approval programs. You got to submit all this information, submit drawings. The bad part is some state agencies, they may not know the codes as well as some other states, or some of the agencies may not know the codes as well as some others, so they may be asking for something different. We're all pretty much falling within the same codes. It shouldn't change much, but it does from time to time. The other thing is when it comes to the air conditioning, the efficiency of the air conditioners have to increase. The motor efficiency, that type of stuff is increasing. They're not changing refrigerants as of, haven't looked at 2022, but before it's mostly motors, fans, the efficiency of the unit, and the EER rating is actually increasing as well. So there is a different set of codes for residential versus commercial. We fall into the commercial and follow that path through. Now, keep in mind, with these codes, they're really only worried about the building itself, the structural portion of the building, the lighting, and the air conditioning. And or if you have plumbing involved in it, say you put a sink in a shelter or a floor drain. They're not worried about the analyzer. They're not worried about the sample systems. They're not worried about any other equipment in that shelter, only with what those pieces are. If you go and make some changes to that, you have to go back and make some changes. But that's really all they're looking at. So you could effectively buy an empty box building, pre-approved, if you will, and then go put your equipment in it. But if you bring it back into the panel board or change the air conditioner, you have to actually go back through a different process. So there's a lot of things here to digest. There's a lot of things that actually have to happen. And weighing through those and what's possible to change and what's not possible to change. Just lastly, I just threw this in. When it comes to the NEC, most states keep up with that, so it's not a big issue from that standpoint. They're a lot more current with that than they are with building code requirements. So whenever time comes, if you have questions, we can talk about that of where there could be possibly variations. Okay? Thank you.
Okay, our next guest works for ExxonMobil. I know his dad real well. So Marco Puzic is with ExxonMobil, and he's going to be talking a little bit about what he sees the impact of these rules. That some of these I've never heard of before, so I'm sure there's going to be some questions after this. But Marco, go ahead.
Yeah. Thank you. So we got a few minutes. So I was asked to participate in this roundtable discussion on the impact of these regulatory requirements on our facilities. So I'd like to encourage the audience to come and let's engage in that roundtable discussion. So I didn't prepare anything. I really want to make this a conversation between the folks that are here, from the vendors to the end users, and maybe together we can brainstorm and come up with ideas on how we can best deploy these projects for environmental, to meet the regulatory requirements. These regulatory agencies and requirements that come, they're not going anywhere. They're always going to be here. It's our license to operate. So, it's on us to meet those requirements in the most efficient and effective, cost-effective way. So my background, as mentioned, I work for ExxonMobil. I live up in Canada, in Calgary, Alberta, so most of my experience with regulatory analyzers and systems have been in the context of the Canadian government. Quite often in Canada, we look to the US EPA, and a lot of our regs are very much model identical to or similar to the US EPA regs. So where I wanted to take the group discussion, I was just thinking of, okay, what are the areas? What are people, processes, and products? So, when we're looking at a regulatory project, can anyone tell me who are some of the people that are involved in executing such a project? So I'm going to pick on someone. Stuart, I'm going to pick on you because you volunteered me to be up here. Who are some of the people that are involved in a regulatory project that you need to collaborate with?
Okay, I'll start with that one. How about project engineers? How about the licensing? How about the community? How about the people who are working on it, the technicians that are going to have to work on it? All of you are going to be impacted, from the manufacturers to the people who make the equipment, to the people who have to put it in, and to the people who have to maintain it. I am lucky. I retired from Shell, but believe me, I had a lot of environmental projects that we ended up doing all on flares, subpart J, subpart JA, all of those things. And what I'm hearing is scaring the crap out of me, and I'm retired, is the stuff that he was talking about, or that Troy was talking about, this fence line monitoring stuff. I think California is dealing with it. Could you give a little bit of all of the stuff that you've had to deal with, Andy? It's tough. It's not funny. It's not easy. And you know, I know a lot of people sit there and they think, oh, the manufacturers, they're licking their licking their lips over this. Not so. I can tell you from the manufacturing standpoint, they don't know how to do it. This is equipment that we're coming up with as a community. When you're looking at what, part per billion for fence line monitoring, how are you going to do that? Put in a mass spec with 36 points? I don't think so. You're going to have to do it open path. How are we going to get there? What is the equipment that's out there today? That's what this forum's about. I've said my piece. I'm retired.
No, thank you, Wes. And you know, I think in those groups of people, all of those, the vendors, the regulator themselves, the end users, the key there is communication, making sure that the regs are understood, that there's feedback from industry to the regulatory body. I can speak for the Canadian region. There has been that dialogue, and we're fortunate enough to have one individual who sits on the ministry in Ontario who is a former analyzer engineer at one of our facilities. So he understands what the challenges are, and we're able to communicate that and get some compromises for what technology we're going to select, how are we going to validate these equipment, how are we going to RADA this equipment, and so forth. So I think that's the key, is having forums like this where we can, for the people aspect, is communicating and building that relationship between all of those interested parties. Next thing I think the area is processes. So how do we execute? You know, first off, I think Troy was touching on it. What are all of the processes in our facilities that we want to monitor? Is it water, air, flares, et cetera? So looking at what are the techniques that we can use to do that. Even processes internally, like when we install this equipment, how do we do our validations? How do we do our RADAs? And I think it's important as a community, we kind of standardize and agree on what is the right process to validate all of our equipment and ensure everything is working and meeting the regulatory requirement. Any other thoughts on processes or? Yeah.
Lively crowd.
Yeah, and I think
Realize after lunch is tough, people.
Yeah. Okay, well, I think finally the product. Looking at all of the different technologies just out here in the hall, I think there was 75 different vendors representing. A number of those equipments are used in continuous monitoring systems. From the end user perspective, we're always looking at what new technologies can we use for those SEMS requirements. We're looking at TDLs in many applications for SEMS where we hadn't used that in the past. Open paths were presented here today, or the other day. Mass specs is another one we've you know, historically in our company have been hesitant to deploy in process operations, but we've deployed mass specs a number of our flare monitoring. So finding the right product to measure for a given application, I think, is key, and sharing amongst the community on which ones work well in given applications, I think, is important. So yeah, open for discussion.
couple of things I can think about. So first we were talking about monitoring chemical species, right? In one area, and then what James was talking about was the changes in building design specifications. I can think of two things. Well, I'm back first in environmental. I worked for Chevron back in the 90s, and ended up working with the South Coast Air Quality Management District on the reclaim rule. Okay, there were a lot of things about that requirement that were chemically not possible or physically not possible to work, and we ended up having a committee of people from Chevron, Shell, I think it was ARCO at the time, a number of others, meeting with the South Coast Air Quality Management District to go over the rule and say, this is feasible, this isn't. What do you try to get out of this part that isn't, that we could give to you in another way? So we ended up negotiating out some of these requirements. Even back then, even the EPA proposed something they called the CAM. They wanted us to measure mercury on stacks. Like, I think back in the 90s, we were looking at inductively coupled plasma spectrophotometers. I'm like, oh, this will go on a stack just great. So we got some of the rules made more reasonable because of having interactions with these agencies. And for a brief time, I was actually a government employee. I actually was worked with the EPA on their science advisory board. And they do listen to industry. I'm not coming in as a, what do you call it, a lobbyist. I'm coming in as an engineer. I think the other, to what James was talking about, well, we all know about the TDLR here in the state of Texas, right? And the uproar that caused in our design for analyzer shelters, and watching our integrators go, oh crap, this is not real. And it's maybe shaking out. And mine, I am so lucky the analyzer shelters I put down in Corpus Christi don't have doors. Yes, thank you. But that's where I think our advantage is. I think back to environmental, I found when I worked for Chevron, we had a liaison with the Air and Waste Management Association that was really valuable, and it gave us the chance to be with people from the EPA on the science side. They're reasonable people. I mean, the science folks are cool. I mean, you talk with other chemists and engineers, and you could say, I can't do that, okay? Yeah, they said, yeah, but when it goes up to Washington and gets the red border review, everything changes. The politicians get a hand on it. Well, that's fine, but let's get the science right in one place. I think the thing that James is talking about, I look at the workshop that we held at Monument Inn. Monument Inn? Yeah, Monument Inn was a great example of how you spread this information about these design changes in shelters and what does it mean to you. And by the way, Wes, I think you left out a group of people who are impacted. You talk about maintenance, and understand, it's super important, but it's also the business owners who are gonna have to pay for this stuff for the next 50 years, okay? First time they get a bill for a replacement laser that could cost $20,000, they're gonna go, you didn't tell me about that. Like, oh yeah, we gotta tell you about that. So anyways, that's my 2 cents.
Thanks, Dan.
Yeah, just to follow up on your comment about different processes and stuff like that, one of the things that strikes me as just going to be getting wilder and wilder is data collection, data projection, data retention, reporting. I mean, we're already hearing reports of areas where environmental information has to be publicly posted online on a website. So when you start adding that with the fact that a lot of industrial processes don't like to have external internet connection processes, it starts putting a lot of us together of, well, how do I go through firewalls to meet this requirement while they don't allow me to do that type thing. So those are the types of things I think that are going to start to really bite us if we don't put some thought into it of suddenly now as a vendor or supplier, I have to put together web pages for you, perhaps. I don't know. It's just wild.
My opinion on that is that that is also a portion of this problem.
Yeah.
I mean, people, it's not just what Troy brought up, and it's not just what James brought up, and it's not just what Mr. Prusick brought up. It's So that's why it's important to have these forums like this. I realize this is at the very end of the thing, and maybe we should do it at the beginning. But it's a forum where people can understand all the processes that are involved here, and that are going to impact you. All the processes that you're going to have to deal with. Right, Andy? I'm looking at Andy Foreman here because I know that they just went through all of this in California.
Every 5 minutes, we update the data in California, fence line monitoring, 5 minutes to the public.
Of course, it goes up to Washington first, and then it comes back. So, I mean, the question is fence line monitoring. Like I said, I'm glad I left because it's a different world. It's a different world today. Yes, sir.
Hello. Derek Waterman. I work with Chenier as a reliability engineer. For us, we are experiencing a new air permitting requirement, particularly on Title 40, subsection B, which refers to the Performance Spec 9. So for us, we have quite a few PGC 1000s on our flare lines, and so we, like you said, who are the main stakeholders that are involved? Of course, project engineering, HSE, reliability, the technicians. Everybody has those vendors. All of these people have a stake in all of this, in this project. So for us, since this is kind of new, we're actually kind of reaching out, and this is one of the great things about having this forum right here is getting more information on this Performance Spec 9, particularly the sample timing, the RADA, all of that stuff. So I'll probably reach out to you afterwards. So thank you.
Well, Wes, you brought up fence line monitoring. So yeah, over in the Bay Area, San Francisco Bay Area, AQMD over there, we had to comply with the setup before the technology even existed. Yeah, that was real fun. Our H2S, those long path length beams weren't something we were able to get, and we had to build the structures. Went through it shifting, and we're talking about 8-inch I-beam that moves very slightly, but when you're talking hundreds of meters, it's quite a feat to try to make it stay working, and then add fog. It just keeps going, and publish it to the entire world. So that's a real tough one. The folks that want us to put these in don't necessarily understand the physics behind the readings. They just want the readings. So when you're at a refinery on hilly terrain and they're shooting across a valley or a gorge or something and they think they're going to get H2S, well, they're just looking at the number. Of course, that's going to be the best reading they get because they ain't ever going to show anything, even in parts per billion. But they're just looking at the number. They don't seem to have a scientist that's looking and saying, hey, this is a valid reading. You know, they don't get it. So somebody told them they had to do it, and they're making us do it, and that's just the way it is. That's how tough this is. I also understand coming down the pike, we got one you folks didn't mention about greenhouse emissions on steam vents, including deaerators and SMR vents. So that one's coming up, I hear, in the future. I've been asked to already scope out something to read these type of readings. So that's going to be a tough one. So just as a warning, that's one, I'm not sure what the subpart and all that is when it comes to it, but I know it's coming.
Okay, I'm going to do something that I don't normally do here. You see that guy that's sitting on the end of this table over here? I used him for Shell, period. He has worked in just about every Shell facility, and it's probably because of me. But all I would tell you is if you don't know what you're not dealing with, you need to go to the experts. Now, you can choose Troy, you can choose whoever you want to, but all I'm telling you is that's the man I used. So, but I'm retired, remember?
Thank you for that endorsement. I do appreciate it. as far as aspirational goals, and when I talk to the EPA, that's exactly the word I use. They're putting numerical values into rules that are aspirational. And the one that is just last week is the new ambient air fence line monitoring rule for ethylene oxide. The action level, the level at which you have to start doing things like engineering additional controls and whatever. The action level, 111 part per trillion.
Feedback, our concerns, and practicality of some of these requirements?
At the state levels, yes. At the federal levels, it's close. It's nearly gone. So these are federal rules that I deal with mostly, and the opportunity to discuss is gone. It's not like it was 25 years ago, for sure. There is no longer that process. In fact, it's amazing that a rule of the magnitude that just came out 2 weeks ago, nobody in this room ever heard of it. There was no trade association participating in the crafting development. It's a proposed rule. Now you have an opportunity to comment. So they are working in their own little chamber, and then it's poof, there's the proposed rule. You have 30 days to comment on it. It's really striking. So I don't know if I would say they're willing to work together, not like we used to see them.
I'm going to come back to this is there's many states, attorney generals that have filed lawsuits on the EPA for doing exactly what you're talking about. That they are not supposed to do this. They are supposed to come to the industry and see what the impact is going to be. So I see this in court. I don't know if you guys, that's my perception.
You'll notice in the flare section of the new chem sector rule, they provide a cost-benefit analysis. How much do they think it may cost to instrument a new flare? And there's maybe 1,000 of them in this new rule. They estimate, $86,000 for this and $10,000 for that. So on average, $100,000 per flare. I can tell you from the last at least 10 years of doing the refinery and ethylene implementation, the average flare, temperature, pressure, flow meters, ultrasonic flow meters, right? These are not cheap things. All the analytical work, where are you going to put them, the shelter, you put that all together, it's a $2 million plus per flare. And that's an easy flare. That's an easy flare. So where the EPA comes up with their cost-benefit numbers make no sense. And we've been commenting on this for a very, very long time, yet they still use their $86,000 number.
My perception on this is that the end users have to push back on this. I mean, this is just getting crazy. That the end users are going to have to push back on. It's not going to be the manufacturers. It's not going to be Troy. It's going to have to be the Shells, the Totals, the Exxons, the Chevrons. The end users are going to have to push back on this. And the only way that I know to do it is go to the attorney generals of your state. That's the only way I know. So.
Yeah, but Wes, if I may comment, to that point, dealing with the state agencies, a lot of times they'll go, well, they've got plenty of money. Well, who really pays for that? They read the big taglines that Exxon or whoever made X amount of billions of dollars. They've got plenty of money. But really, it goes back to the consumer as well. So everything passed through. So you're hitting the consumer with it anyway. But that's their approach a lot of times. Well, they've got plenty of money. It's not a problem.
I'm just curious if you guys don't have an industry advocacy group. In Western Canada, we have a group called the IMG, the Industry Measurement Group. They work with CAP and the local environmental agencies in Alberta particularly, but also in Saskatchewan and BC, and basically liaison between industry and the various regulatory bodies for SEMS code changes, methane emission monitoring, all that sort of stuff. Is that not something that comes into play here in the US?
Oh yes, there's many trade associations, a whole variety of them.
Not trade per se, it's really the industry itself. So it would be the Exxons, the Shells, so on and so forth, that kind of band together to review upcoming legislation, provide feedback to the EPA directly, and negotiate where that's going. But it doesn't sound like that is really a negotiation, or is that just the way it is? Okay.
Yeah, there's a good example, Rod, of the recent Alberta SEMS code update where it was issued out for industry comment, and then they issued a document summarizing those comments, and I was quite surprised. There was quite a few accommodations from the original draft proposal to the final draft, so that just signifies that they took the input, listened, and made the compromises necessary. So yeah, I don't know what the process will be for this one. You say you have 30 days to comment. Is it what's the process of who gets invited to comment? Is it open to anybody in the public?
You have to search it out then.
Yeah.
It's in the public registry in the federal code, so it's made public. Give you various timetables to reply. A lot of companies in this room do reply. Your environmental organizations, departments do give responses.
So I guess one other thing that kind of doesn't bother me, but it's like, what are we going to do? And I keep coming back to the requirements around fence line monitoring, because I know you're running into a lot of these issues. What's out there? I mean, from a vendor standpoint, I don't see any vendors raising their hands saying, I have a solution. There's one.
I actually want to say the opposite. I want to say that I think the vendors here, and I'm a vendor, I think the vendors here have to give their view, because, speaking on behalf of all the vendors, the last thing I want to do is try to solve an application problem that my technology is not able to do, or indeed to apply a technology for a measurement that I see as being nonsensical and bringing no value. Okay, and I would like to think that the vendors have integrity to want to play a positive role in this process.
I believe that they do, but that's the reason why I'm worried just a little bit, because I don't know how some of these processes are going to be done. I really don't. And like I said, I'm retired. I've been retired for a while, but I know that fence line monitoring was coming up, and we had no clue. We thought open path, we thought point source, we thought all sorts of. I know that I was working with Andy before they became another company. So I would urge our scientific community to get involved. And what I mean by that is the smart people sitting in this room, because I'm not one of them. Just letting you know. I'm limited in that regard. Go ahead.
Yes, Cliff Gordon with M&C Tech Group. So our company does supply some OpenPath H2S monitors. I can speak to what's on the periphery around those, some OpenPath UV for BTEX and some OpenPath FTIR, and then of course there are some other point source monitors. So being out there in the land of crazy California, which is where things like this start, the Bay Area Air Quality Management District, they implemented an OpenPath monitoring rule. And from what I could tell, and I came in after the fact because the H2S monitors were not working well, so they gave an extension period on that. But in the beginning, if you want to talk about a half-baked way of doing things, is they just wanted to get a regulation in place. So where they started was they put a regulation out there, and then they said that they're going to follow the manufacturer's QA procedures and then believe what the manufacturer's data sheet says. Various manufacturers have various levels of what they consider good science or integrity, but there hasn't been any, whether it's integrity or lack of technical expertise, the various things ended up out there, and it was really, in my opinion, a real kind of halfway baked thing of doing it. But now, down in South Coast air quality, they've implemented some third-party auditing of the, of these monitors. Me being from a source level, monitoring with, process analyzers and SIMs. There was QA for SIMs that was well known, daily drift checks and QA, QC checks, all these other things. For OpenPath, when it started, there was none of that in process. Right now, Bay Area AQMD and South Coast AQMD is starting to implement the QA processes, which actually is starting to make it a real measurement that, whether it's necessary or not, or what gases are necessary. I have my own opinions on that, but I'm not a regulator, so I don't make those decisions. But I can say that having data that is, has some kind of QA QC process to it, that out in California and I believe out in Colorado, they're starting to implement this process, which means that the actual data itself is going to mean something, as opposed to just believing what any salesman tells you. But OpenPath is new, certainly new, and when we put our equipment together and started testing it a few years ago and designing it, we were designing it with having the data being, the QA process actually being able to defend our data and talk about how we decide whether it's valid or not, how we do bump tests and linearity tests and things like that, kind of similar to a point source environmental measurement. But anyway, that's kind of my 2 cents worth. Is it had been kind of a half-baked thing. It has been, and it's in a transition period right now where they're starting to have third-party auditing of the QA for each system and the data and what that means. So it's kind of in that stage right now in California anyway, where they're transitioning to third-party audits of it, which makes the data more real, irregardless of whether the measurement itself makes any sense or not. Yes, sir.
I'm going to, a few years ago, there was a gentleman that just walked into the room that gave a keynote address at a banquet that I was at. And one of the things that, there was many things that I got from that keynote address, but the one thing that I always remember from that keynote address is that an environmental group never engineered the way out of a paper bag. And that's what's happening is we have, and there's another Texas governor that liked to say the prisoners are running the jail. So that's where we're at. I think that's what's happening a lot. It's very frustrating. And I know that the people that are sitting in this room are the ones that have to deal with it. So kudos to you. I'm going to cut this short. Do you guys have any more questions or anything like that? We're going 15 minutes over. No more questions?
Yes.
Oh, no.
I got about five pages of questions here and comments. James, I'm not going to talk about TDLR because they just scare the crap out of me. They don't know what they're talking about. There's nothing we can do about it. But thank you for telling me I've got to change my lighting and stuff like that. I want to talk more about what Troy was coming on with, some of these rules that just keep coming and keep coming and keep coming. I mean, I can think more about flares and cooling towers because those are our two big outside of Sims. Sims is easy. Sims is easy. I'm sorry, guys. It just is. Flares and cooling towers, not so easy. Some of the things we're having to deal with. So now we're being asked, because it has to go into the permit, what's in your process? I don't care how much or how little, what's in your process. So we're a big chemical producer. It's mostly ethylene, it's propylene oxide, but there's always small cats and dogs from the chemistry that gets in your process. They want to be able to measure that. And if you look at the mass balance on a cooling tower application, for example, you look at the mass balance, and I might have, I don't know, throw out a chemical acetone. And it's in the process at something like 4 pounds an hour going to the flare out of 60,000 pounds. Pick a number, and by the time you back calculate that to a ppm, there's nothing out there that can detect it. But I got to measure it because it's in our process, and now it's in the permit. Well, if I can't measure it, I'm required to report a value below the minimum detection limit. So I have to actually report a value that can't be there. So now I need, from our vendors, detection limits that are lower and lower and lower and lower to stop me violating a permit by reporting a number that can't possibly be there. It's just something to think about. And GC manufacturers talking to you as well. And then flares, I mean, there's so many different ways to do a flare. But I haven't found one yet that meets all of the requirements of 15-minute update time, BTU control, and now hydrocarbon to steam control for your smoking thing. What about the incipient smoking? How does that come into play with the smoking rule and the visibility? I mean, you have to speciate everything, and it has to be instantaneous.
The result of an ongoing open lawsuit that I like to track, where the environmental groups, the NGOs, are telling EPA that the application of 99% DRE or 98% DRE on a well-operated flare isn't good enough, because they say kinetics professors and engineers and scientists can tell you that burning pure, sweet, clean, virgin natural gas, if you burn that, you will create every molecule known to mankind in the products of incomplete combustion. So that 2% that is not being combusted, you guessed it, the word on the street is they want EPA to make a rule that requires us to speciate the non-combusted materials coming out of your flare. So the way it works today is if you have a cyclohexane unit and you're sending cyclohexane to that flare, take 98% of it, destroy it, you report to the TCEQ 2% uncombusted cyclohexane. That's what you report. Now, we're all smart people. We all know that it's not cyclohexane. It's a whole list of, it's the Perry's Chemical Handbook of everything you can imagine, right? It's everything. But how are you going to come up with emission factors now based on your process to speciate those, what we call PICs, right? The PIC. Good luck. I mean, if that makes it into a flare rule, which is under discussion right now, if that makes it into a flare rule, that's going to be wickedly complicated for fence line monitoring, because now people want to look for each one of those PICs that you just listed off. There, more bad news. Where's Wes? Sorry, Wes. More bad news.
Okay. I'm going to cut this off because I know that we have a lot of people that are here. They want to know what the product of the year is. Stuart, would you please come up? I heard something, Dale, I don't think you were in here when it was brought up, but Troy had brought up that maybe Monday next year, which I believe is in the slides of when we're going to be coming here next year. That Monday, one of the secondary advanced training classes that would take place would be around modeling and some of the environmental stuff that Troy had talked about. And I'll get with Troy and find out exactly where he was going with that. But that may be something that we can do as far as another advanced training class, because from an ATC standpoint, we were looking for different tracks, because the advanced training that you're getting with the ATC is some serious discounted training. And so my thing to all of the Shell people sitting in here is get it in your goals that you want to attend this meeting, because this is where you're going to find out the most, and you're going to get the best training. So, with that said, I'm going to turn this over to. My mind just went, Stuart.
All right. Well, thank you. Everybody hear me okay now? Good. We're still listing in this ship, I think, a little bit, but that's okay. Thanks for making it to the end. We really appreciate everybody staying right to the very end. It's very important for the panel that we just had and the presenters that came this afternoon. We thank you for being here. We hope you had a great week. We really do. We really hope it was worthwhile. I would ask you when you get home tonight, look on your front lawns. If that British flag is there, you're welcome to the British Empire. That's how it works. We snuck it in. The bills will be in the post for your VIG. It was a fantastic week. We had a lot of great feedback. I would hope that my friends here would tell me if it was negative feedback. We certainly would welcome that too if there is any. But we've had some very tremendous feedback. We had a good colleague of ours from Europe who I asked why they were here, and they said, this is the best analytical collection of people in the world. So if that's true, I hope it is true. That's a wonderful feeling. So that's why we do this, that's why we're here, that it's just our analytical community, undiluted. There is some conversations about the environmental wing of what we do, the laboratory, potentially some versions of the laboratory that exist within the plants with what we do. The natural gas world, we could do a little bit better with that. They are represented in other places, but we'd certainly like to have them with us here if we could, so that we'll welcome that feedback too from anybody. If you see other parts of the business that you work in or sell into that you would like to see represented here, we'd certainly like to have those people here. For anyone that stuck it to the end and is brand new, we really hope it was great for you. I see a lot of very, very familiar faces, which is wonderful for me. But I'm happy that we see new faces too, and we've had one or two people come up to this week and said, first time here, really loving it, this is amazing, how come everybody knows everybody, how come I never heard about it before? And we're trying to change that a little bit, be a bit more focused through ATC rather than being part of this bigger organization at ISA. A couple of quick highlights and the date for next year. We were asked a number of times over the period that they'd like to know earlier and earlier and earlier when the show is. And the truth is that Dale books the show pretty early. It's already booked. So these are the dates. They are there. We will put them up on the website in fairly large numbers so you can see them. And we will remind people as regularly as we can through the website, through LinkedIn, various other places that is the date, should people need to get in early with their bosses to get approval for travel for next year. So that is the date. It is back here. We're very happy to be back here. We have some ideas about moving around again. And again, we would welcome anybody coming forward to talk to us about moving it around. We are a big machine now, as you can see. So not all places can fit what we do. We need a conference hall. We need a fairly large auditorium. We need lots of hotel space. So that does rather limit where we go. So that is one of our constraints when we think about where we want to go. The other one is making sure that we get all the right people coming and that you're welcome to come, that you're happy to come to that venue, wherever it is, and that we get a lot of end users. Everybody wants to see the end users here, so we happily like to do that. The third constraint is that it's not too much fun that nobody shows up on day 2 because they're all whipping it out on day 1, nighttime. So there are a couple of ideas about where we want to go, but we are thinking beyond 2024 that we might move it around, right, Wesley? And if anybody's got any ideas or recommendations, then that would be great. When we move away from this place, we need somebody on the ground. So the cautionary note is if you come tell us where you want to be, we better hope you might be our person on the ground when we get there, just to help us out. A quick teaser about the website. So we're doing everything we can, as best we can, to give you more information quicker and to build on that idea. As you saw from this year, we were very lucky to have Jaden, one of Phil's personnel, to come help us build our own website, and we have plans to expand that website. We'd like to not just leave it fallow, as we often did in the past until the event came around again. We will start adding things in there. We will start building ideas. And I put a few up on the slide here today just to give you a feel for that. And again, we will welcome all ideas. But these are some of Jaden's ideas for what we would like to do in the future. Streamline the information collection, maybe make user accounts. So when you sign up, you become a user of ATC. A place for the papers to be kept. Everybody will be sent the papers this year, but thereafter we will post them up there for people to be able to download. That seems to be one of the good ideas. In the interim, we'd like to do blogs and newsletters, perhaps even some technical forums, maybe even some webinars, perhaps if our willing audience is happy to come and step forward. We will put a vendors page up there for more information about what the vendors do, and we will definitely have a volunteers page. You can see who the people are that chair all the portions of the volunteer group, and we will welcome anyone to come forward. We're thinking about a program on how we roll in and out of this role so you don't have to listen to British guys again and again and again, year after year after year. So please look in on a regular basis. Please come check it. We will do our best to update it regularly for everybody, and we certainly have all the dates and all the ideas running for next year. Quick thank you to the team. This is the team that shows up week in, week out as we run up to the event. We start usually every 2 weeks, and then we run up every week. And then during the course of this week, every one of these people has been busy helping out. And we truly, truly are thankful for everything that they do for us, because it is a lot of work. There's a lot of work that goes into this. We love doing it. We like to give back. My old friend Randy Howard, that I used to work for, told me we're an intellectually generous community, and I like that idea. I truly believe it to be true. There are many people in here that are happy to give time back, and that's a wonderful feeling. The last thing is, we're not done, of course. Anyone that would like to do hands-on training, these are the trainers for tomorrow. There will still be slots available, I'm sure, and if you decide you want to stay one more day because you need a couple more beers in the bar tonight, please sign up for one of these guys. I'm sure you can still find them kicking around, or we can help you at the front desk should you want to do that. All right, here's the good stuff, and I'm going to hand it over to Paul. We'll start with Product of the Year, Paul. You're not doing it? You're doing it. Wesley's doing Product of the Year. The winner is?
No, I'm going to say a little bit. I talk a lot. I want to thank the end users that this was a secret team. There was 9 individuals. That way you don't know who it was or how they did it. They were all end users from all major branches of the oil and gas industry. We had engineers, chief people in their industry. We had specialists. They were all specialists, and they were all engineering specialists. So, with no further ado, the winner is Air Optics, Gas Eye Extractive Analyzer. Can you come up? Come up.
Come on up, Paul.
I will only tell you that from the people who were involved in the choosing of this was the #1 of all of them. It was unanimous. And that is unusual because you guys all know you can put 2 analyzer engineers in the same room, give them a problem, they come up with 2 different answers.
Well, I would like to thank, I'm very surprised that, our effort was appreciated, that, coming from European company, to have this product of the year in the United States is really, I really appreciate that. So I hope, you know.
Welcome. It's your job to do, not ours.
Okay, thank you.
We will have a portion of the website that'll have that up for you as product of the year. Absolutely. Thanks, Pavel. Congratulations.
Thank you, Paul. And I'm just going to have to say that throughout the whole course of this, I've been going up, reaching, and grabbing hold of Paulo and telling him he had to be careful who he was talking to. He's a likable guy.
Okay. Okay, so we'll move on now to papers of the year. And this time I will hand it over to Paul. Do you want me to be your Vanna White here? Do you want to? I don't know. What have you got up here? So here's the details. That's how they are done. First, second, and third.
All right. You read that one yet?
There you go, sir.
All right. If you've read that one, we can go to the next one. So the process, I mean, people don't just get up here and talk. They have to write a white paper, and it's peer reviewed, and those will be posted, I think, on our website next year or at the end of the conference, Wes? Yeah, okay. The presentations, if you want the actual PowerPoints, you'll just have to get with the individual authors because they control the PowerPoints. These are the 5 people that did the peer reviews. And when you think about reading 25 papers and making comments on them, that's very time consuming. So I really want to acknowledge these guys and the amount of time and effort that they put into it. And in particular, that Bark at the top there, because he became the team leader at very, very short notice. So special kudos to Bark Fu. I guess that's the process. So we're going to move to the next slide. The third placed paper was presented by Edward Orr, authored by Edward and Henry Lin, entitled Low-Level Gas Analysis in Process and Area Monitoring. And if the author is in the audience, he can come and get his envelope. Thank you, Ed. These top papers were all very closely scored together, so it was a fine line between the top 10, really. Okay, so go to the next slide, and it's a second place paper. Mike and Al, Challenges and Benefits of Standardizing Process GC Applications. I think Al is here. Mike had to leave. Thank you, Al. Do we have drum rolls? Phil.
Gotta quit winning.
Okay, Phil, you give a good paper, you write a good paper, the audience and the tech review team recognize that. You had the highest scoring technical and the highest scoring audience. So Phil and Kevin Harris, what's the scoop? Advances in process sampling. So the moral of the story is, if you want to win, you need to contract Phil to write and present your paper for you.
That's all we have, folks. Thank you so much for a fabulous year, and we'll see you in 2024. We really appreciate it. Thank you.
Thank you so much for coming. Thank you so much for coming.